What if making it to Mars is the easy part? Imagine standing on the surface of another world, red dust at your boots, a butterscotch sky above you, and somewhere behind you, 340 million kilometers away, everyone you have ever loved. Engineers and mission planners are quietly arriving at a conclusion nobody wants to say out loud: you are probably never coming back. If you love exploring ideas like this, make sure to give this video a like. Now let's get started. Getting to Mars is hard. Getting back from Mars might be, with everything we currently have available, close to impossible. Here's why. Space travel is nothing like driving a car. You cannot just stop, turn around, and head home whenever you feel like it. Every single movement in space costs fuel, and fuel is heavy. Heavy things are brutally expensive and dangerous to launch. The rocket equation, a formula that has haunted aerospace engineers since the early 20th century, tells us that the amount of propellant you need grows exponentially with the mass you're trying to move. It is one of the most punishing constraints in all of physics, and no amount of cleverness or ambition can make it go away. When a rocket leaves Earth, it is mostly fuel. The actual payload, the spacecraft, the life support systems, the supplies, the crew, is a relatively tiny fraction of the total mass sitting on the launch pad. By the time that vehicle reaches Mars, nearly all of that propellant is gone, spent. To leave Mars and head back toward Earth, you would need either a second fully fueled rocket waiting for you, launched from Earth ahead of time and already sitting on the surface, or some way of manufacturing fuel directly on Mars using local resources. And neither of those options is trivial. They represent enormous engineering challenges that no mission has fully cracked yet. The distance between Earth and Mars isn't fixed. Both planets are constantly moving through their orbits around the Sun, which means the gap between them changes dramatically over time. At their closest approach, a moment astronomers call opposition, Mars sits roughly 54 million kilometers away. At the opposite extreme, when the two planets are on opposite sides of the Sun, that distance swells to over 400 million kilometers. A one-way trip, depending on exactly when you launch, typically takes somewhere between 6 and 9 months. And here's a detail that changes everything. You cannot just launch whenever you want. There are specific windows, called launch windows, that open approximately every 26 months when the planets align in a way that makes the journey reasonably fuel efficient. Miss one of those windows and you are sitting on Mars or in orbit, waiting more than 2 years for the next opportunity to leave. That's not a delay. That's a life sentence measured in Martian years. So if something breaks, if a system fails catastrophically, if a member of the crew develops a serious medical condition, you cannot call for rescue. The time it takes for a signal to travel between Earth and Mars ranges from about 3 minutes at closest approach to over 22 minutes when the planets are farthest apart. A simple back-and-forth exchange, a question and an answer, could eat up close to 45 minutes. In an emergency, that is an eternity. You are, in every meaningful sense, alone. By the way, what we're exploring today connects very directly to something I covered in another video, exploring why Mars would be a horrible place to live. That video digs into the day-to-day brutal reality of existing on the Martian surface. The toxic soil, the unbreathable atmosphere, the temperature swings that would kill you in minutes without protection. It's on the card above, but it's the perfect companion to what we're unpacking today. The link is also in the description and pinned on the comments. But what we're focused on right now is something even more existential. Not just whether Mars is uncomfortable, whether the people who go there could ever physically leave. To understand that, we have to talk about the human body. And this is where things get genuinely sobering. Your body is the product of roughly 3.8 billion years of evolution on one very specific planet. Every system inside you, your skeleton, your heart, your immune defenses, your sense of balance, your capacity to process oxygen was built and refined for one precise set of conditions, one gravitational pull, one magnetic field protecting you from above, one atmospheric pressure pressing in from all sides, one rich ecosystem of microbes you've been co-evolving with since before our ancestors were recognizably human. You are, in the most literal sense, a creature of Earth. Rip a human being out of that environment and place them somewhere radically different, and the body doesn't just struggle. It starts to dismantle itself. Let's begin with bones. In microgravity, the near weightlessness of space, your skeletal system doesn't need to support your body weight. So it does what any efficient biological system does when it detects a structure that's no longer being used. It starts reabsorbing it. Astronauts aboard the International Space Station, which orbits at roughly 400 kilometers above Earth's surface, lose between 1 and 2% of their bone density every single month. A complete round trip to Mars, accounting for transit time in both directions and a meaningful stay on the surface, could take anywhere from 2 to 3 years. Do the math, and you're looking at catastrophic losses that rehabilitation may never fully reverse. Even with the best physical therapy available on Earth, muscle mass follows the same cruel logic. Without gravity demanding constant effort from your muscles just to stand upright, they weaken rapidly. The heart, itself a muscle, becomes smaller and less efficient. Astronauts returning from 6-month stays on the space station are routinely carried out of their landing capsule because they cannot walk. Their legs simply won't hold them. Now picture that same person after 2 or 3 years in space and on the low-gravity surface of Mars, a planet with just 38% of Earth's gravitational pull, attempting to climb back into a rocket, survive another 9 months of transit, and then re-enter Earth's atmosphere. The physical demand is staggering, and that's assuming nothing else went wrong, but something else almost certainly would go wrong, because drifting between the planets is something invisible, something you cannot smell or taste or feel on your skin, and it may be the most dangerous thing in the entire mission. Radiation. In low Earth orbit, the International Space Station benefits from partial protection from Earth's magnetosphere, the invisible magnetic bubble generated by our planet's churning iron core. That field deflects a significant fraction of the high-energy particles streaming in from the Sun and from deep space. Mars lost its global magnetic field billions of years ago. The scientific consensus points to the cooling and solidification of Mars's liquid iron core, which shut down the planetary dynamo that once generated that protective shield. Without it, the Martian surface sits exposed, bombarded daily by solar energetic particles and galactic cosmic rays streaming in from the far reaches of the universe. NASA's Curiosity rover, which has been operating on the Martian surface since 2012, carries an instrument called the Radiation Assessment Detector, RAD. The data it has sent back is deeply revealing. A human crew making the round trip to Mars and spending meaningful time on the surface would accumulate radiation doses that most space agencies consider far beyond acceptable safety limits. We're talking about substantially elevated lifetime cancer risk, potential damage to the central nervous system, and documented effects on memory and cognitive function, effects that researchers studying long-duration spaceflight are increasingly alarmed by. And here's what makes this even harder to solve. Galactic cosmic rays, ultra-high energy particles accelerated to near the speed of light by ancient supernovae and other violent cosmic events, can punch straight through almost anything: the walls of a spacecraft, metres of compacted Martian soil. Even lead shielding offers only partial protection. Adding heavy shielding to a spacecraft helps, but it also adds mass, which feeds directly back into the rocket equation, demanding more fuel, which adds more mass, which demands more fuel still. It is a trap with no clean exit, so here is the picture as it stands. You've traveled 6 to 9 months through a radiation-soaked void. Your bones have thinned. Your cardiovascular system has weakened. You've landed on a world with a carbon dioxide atmosphere so thin it offers almost no protection from the radiation still pouring down on you every day. And now, to go home, you need a fully fueled rocket, a precise launch window that may be more than 2 years away, a body that may or may not survive another interplanetary crossing, and a re-entry into Earth's atmosphere at the end of it all. This is the reality sitting quietly beneath the excitement of every Mars mission announcement. This is what the engineers and the physicians and the mission architects are wrestling with in rooms that don't make the headlines, and the conversation is shifting. Slowly, carefully, almost reluctantly, the question is changing. It's moving from how do we bring people back from Mars towards something more uncomfortable, something that changes the entire moral dimension of the mission. Should we even plan to bring them back? That question deserves more than a quick answer. And I want you to sit with it for just a moment, because it touches something deep. It touches what it means to explore, what it means to sacrifice, and what it means to be human in a universe that is 4.5 billion years old and doesn't care about our comfort. Let's talk about a word that makes space agency administrators deeply uncomfortable. Permanent, not long duration, not extended stay. Permanent. As in, you land, you build, you live, and you die there, on Mars, tens of millions of kilometers from the only world that has ever produced life, as far as we know, in the entire 4.5 billion year history of this solar system. The idea of a one-way mission to Mars is not new. It has been floating around the edges of serious scientific conversation for decades, but something has shifted in recent years. The conversation has moved from the fringes into the mainstream, from science fiction forums into peer-reviewed journals, from late-night thought experiments into actual mission architecture documents. Researchers, ethicists, engineers and former astronauts are now openly debating not whether a one-way mission is conceivable, but whether it might actually be the most rational approach we have. And when you look at the numbers, really look at them, it's hard to argue with the logic. Every kilogram you don't need to bring back to Earth is a kilogram you don't need to launch from Earth in the first place. And on a mission of this scale, every kilogram matters enormously. Studies published by researchers at places like MIT and NASA's Jet Propulsion Laboratory have consistently shown that a one-way architecture dramatically reduces the mass, the cost, and the engineering complexity of a crewed Mars mission. We're not talking about a marginal improvement. We're talking about a reduction so significant that it could be the difference between a mission that is theoretically possible and one that is practically achievable within the lifetimes of people alive today. The late cosmologist and science communicator Carl Sagan once wrote that humans are by nature wanderers, that our ancestors who stayed home, who never crossed the next ridge or sailed beyond the known horizon, are not our ancestors in the spirit that matters most. The ones who went, who ventured into the unknown with incomplete information and imperfect tools, and the very real possibility of not returning, those are the people who built the world we inherited. And now we stand at the edge of a new kind of horizon, one that is measured not in days of sailing, but in months of interplanetary transit, one that is not defined by oceans, but by the cold vacuum of space itself. So who would actually go? This is where the psychology becomes as fascinating as the physics, because the kind of person who would volunteer for a one-way mission to Mars is not the person you might initially imagine. Research into the psychology of extreme explorers, drawing on studies of Antarctic expedition teams, long-duration submarine crews, isolated polar researchers, and analog Mars mission simulations in places like the Utah desert, and the slopes of Mauna Loa in Hawaii paints a surprisingly nuanced portrait. The best candidates are not reckless thrill seekers. They are not people who don't value their lives. Quite the opposite. The individuals who perform best in conditions of extreme isolation, high stakes, and irreversible decisions tend to be people with a profound sense of purpose. People who have a framework, whether philosophical, spiritual, or scientific, for understanding their existence in relation to something much larger than themselves. People who can sit in silence in a confined space for months at a time and still find meaning, still maintain warmth toward their crewmates, still do the work. High Seers, the Hawaii space exploration analog and simulation, has conducted multiple multi-month isolation studies inside a habitat dome on the northern slopes of Mauna Loa. Crews of 6 have lived in conditions designed to mimic the communication delays, the confinement, and the social dynamics of a Mars mission. What the researchers found was illuminating. Group cohesion, leadership dynamics, and individual psychological resilience mattered more to mission success than almost any technical factor. The human element was both the greatest vulnerability and the greatest strength. Mars 500, a landmark study conducted in Moscow between 2010 and 2011, took 6 volunteers and locked them inside a series of interconnected modules for 520 days. 520 days. That's roughly the duration of a Mars mission, including transit and surface time. The participants never left. They communicated with a simulated time delay. They performed simulated spacewalks, they monitored their own health, and they emerged physically and psychologically in remarkably stable condition, with several important caveats. Sleep disruption was significant, physical activity declined dramatically over time, and subtle social tensions, even in a carefully selected crew, proved difficult to fully suppress. These studies are sobering. They tell us that the human mind and body can endure the conditions of a Mars mission, but not without cost, not without deliberate design, careful crew selection, robust psychological support systems, and a mission architecture that takes the inner landscape of the crew as seriously as the outer landscape of the planet. Now let's talk about Mars itself, because the planet we are considering sending human beings to permanently is by almost every measure extraordinarily hostile. And yet, and this is the part that still manages to fill me with something close to wonder, it is also the most Earth-like world we have found anywhere in the reachable cosmos. Mars has days. They're called sols, and they last 24 hours and 37 minutes, close enough to an Earth day that your circadian rhythm would adapt with relatively modest difficulty. Mars has seasons, driven by an axial tilt of about 25 degrees compared to Earth's 23.5. It has polar ice caps made primarily of water ice and dry ice, which is frozen carbon dioxide. It has ancient river valleys carved by flowing water billions of years ago. It has volcanoes, including Olympus Mons, the largest volcano in the entire solar system, rising approximately 22 kilometers above the surrounding plains. That is nearly 2.5 times the height of Mount Everest above sea level. Mars has a thin atmosphere, not thick enough to breathe. It is composed of about 95% carbon dioxide, with small amounts of nitrogen, argon, and trace gases. But it is an atmosphere. It creates weather. There are dust storms on Mars so vast and so prolonged that they can engulf the entire planet for weeks or months at a time. When one of those storms rolls in, and they are difficult to predict with current technology, it blocks the sunlight that solar panels depend on. It coats surfaces. It infiltrates equipment. NASA's Opportunity rover, which operated on the Martian surface for nearly 15 years, ultimately met its end in 2018 when a global dust storm depleted its solar power to the point of no return. Mission controllers sent the rover a final command and heard only silence. But within that hostility lies something remarkable, something that, when the MOXIE experiment aboard NASA's Perseverance rover demonstrated it in 2021, quietly changed the conversation about Mars settlement in ways that deserve far more attention than they received. MOXIE, the Mars Oxygen in Situ Resource Utilization Experiment, successfully extracted oxygen directly from the Martian atmosphere. It converted carbon dioxide into breathable oxygen using a process called solid oxide electrolysis. The device was small, roughly the size of a lunchbox, and it produced oxygen in modest quantities. But the principle it proved was enormous. It demonstrated that future missions could potentially manufacture breathable air from the planet's own thin atmosphere, rather than hauling every single breath from Earth across hundreds of millions of kilometers of empty space. This concept, using local Martian resources to sustain human life and even produce rocket propellant, has a name: in situ resource utilization, or ISRU. It is widely considered one of the most important enabling technologies for any permanent human presence on Mars, and it goes beyond just oxygen. Mars has water ice, confirmed in vast quantities just beneath the surface at mid-latitudes and at the poles in enormous frozen deposits. Liquid water, potentially, may exist in small amounts in the deep subsurface, though the evidence for that remains genuinely debated. The presence of water changes everything. Water can be split into hydrogen and oxygen through electrolysis. Hydrogen and oxygen can be combined to create one of the most powerful rocket propellants we know. Water can be filtered and consumed. It can grow food in controlled environments. It is, in many ways, the most critical resource a human settlement could hope to find, and Mars appears to have it in meaningful quantities, so the picture is more nuanced than either pure optimism or pure despair. Mars is not hospitable in any conventional sense, but it is not entirely without resources. The question is whether those resources can be accessed, processed, and utilized at a scale sufficient to sustain human life, not for a week or a month, but indefinitely. Let's bring in one of the most striking real-world examples of how seriously some people are taking this possibility. SpaceX's Starship program is the most ambitious launch vehicle ever developed by a private company. The fully stacked vehicle stands approximately 121 meters tall, taller than any rocket ever built or flown. It is designed from the ground up to be fully and rapidly reusable, with the stated goal of dramatically reducing the cost of reaching orbit and beyond. Elon Musk has consistently stated, in interviews on social media and in technical presentations, that the long-term goal of SpaceX is not simply to reach Mars, but to establish a self-sustaining city there. He has spoken openly about the possibility that early Mars settlers may not return to Earth, framing it not as a tragedy, but as the natural and necessary cost of becoming a multi-planetary species. Now, it's important to apply critical thinking here. Musk's timelines have historically been optimistic to a degree that has attracted significant skepticism from the broader scientific and aerospace community. Promises of crewed Mars missions by the late 2010s shifted to the mid-2020s and continue to evolve. The engineering challenges of Starship, heat shield durability, in-orbit refueling, landing reliably on Mars, and dozens of other critical systems are genuinely formidable. Several Starship test flights resulted in spectacular explosions before the program began achieving more stable flight profiles. The gap between a test flight in Earth's atmosphere and a crewed landing on Mars is almost incomprehensibly vast. But here is the thing: the direction of travel is real, even if the pace is uncertain. The technologies being developed, reusable rockets, in-situ resource utilization, closed-loop life support systems, radiation shielding innovations are not fantasies. They are engineering problems being worked on by thousands of some of the most talented scientists and engineers on the planet. and the question of whether the first humans on Mars would come back is not an abstract philosophical puzzle. It is a question being baked into the actual mission designs being developed right now. And yet, even if the engineering were solved perfectly, even if the rockets worked flawlessly, even if the habitats were safe and the radiation shielding was sufficient and the water extraction systems hummed along without failure, there is still a dimension of this challenge that none of the technical solutions can fully address. The human dimension. What does it do to a person to know they are never going home? Not metaphorically, literally. What does it do to your sleep, to your dreams, to your sense of identity? Humans are deeply social animals. We are wired for connection, for familiarity, for the particular comfort of places we have known since childhood. The smell of rain on warm pavement, the sound of a specific city at a specific hour of the night, the faces of people you love, not on a screen with a 22-minute communication delay, but right there, close enough to touch. Astronauts who have spent 6 months on the International Space Station describe the experience of returning to Earth in terms that sound almost religious. The weight of their own bodies pressing down into a chair, the feeling of wind, the overwhelming richness of natural sound after months of the station's constant mechanical hum. Now take all of that away, permanently, replace it with a horizon of reddish rock and thin, cold air and a sky that never turns quite the color it's supposed to be, and ask yourself honestly what that does to the mind over years and decades. This is one of the most important open questions in all of human spaceflight research, and it has no clean answer yet. Let's start with a thought experiment. Imagine a child born on Mars, not transported there, born there, first breath taken inside a pressurized habitat, under artificial lighting, in a world where the sky outside the window is the color of dusty amber and the gravity pulling at their tiny body is barely more than a third of what you feel right now, sitting wherever you are. This child grows up running through corridors instead of open fields. They learn about oceans from videos. They have never felt rain. They have never seen a horizon that isn't broken by a rust-colored ridge of volcanic rock. And here is the question that keeps certain researchers and bioethicists awake at night. Could that child ever come to Earth? The honest answer, based on what we currently understand about developmental biology, skeletal formation, and cardiovascular physiology, is that they probably could not safely, possibly not at all. Here's why. The human skeleton does not finish developing at birth. It continues growing and reshaping itself well into a person's mid-20s, responding constantly to the mechanical loads placed on it by gravity and movement. A child raised in Mars's 38% gravitational field would develop bones calibrated for that environment. Their skeleton would be longer and more slender than an Earth-born human's. Their muscles, their cardiovascular system, their lung capacity, all of it shaped by a world that demands less of the body just to stay upright and alive. Bring that person to Earth, where gravity suddenly demands 2.5 times more from every single system in their body, and the physiological shock could be fatal. At minimum, it would be profoundly disabling. We have never tested this in a human being, for obvious ethical reasons, but the biological logic is solid, grounded in well-established principles of developmental physiology. And if it holds, if the first generation of Martian-born humans truly cannot survive on Earth, then something extraordinary and quietly terrifying has happened. The species has forked, not metaphorically, not philosophically, genetically and physiologically. Over the course of just 1 or 2 generations, the descendants of Earth humans living on Mars may have begun to diverge into something meaningfully different. Scientists use the word speciation for the process by which one population splits into 2 distinct species over time, typically driven by geographic isolation and different environmental pressures. On Earth, Speciation usually takes thousands to millions of years. But the conditions on Mars, the radical difference in gravity, radiation exposure, atmospheric composition, diet, microbial environment, and even the length of the day, create selection pressures so intense and so different from anything on Earth that some researchers have speculated the timeline for meaningful biological divergence could compress dramatically, not into species-level differences within a few generations, but into measurable, clinically significant physiological differences far sooner than evolutionary biology would normally predict. This is not fringe science fiction. Papers exploring the long-term biological implications of multi-generational spaceflight and planetary settlement have appeared in journals including Nature, Acta Astronautica, and publications from the National Academies of Sciences. The conversation is real, the uncertainty is real, and the implications are staggering. Now let's zoom out from biology and talk about something even more fundamental. Something that underlies every single challenge we have discussed so far and every challenge we are about to discuss: energy. Everything on Mars costs more energy than it does on Earth. Heating a habitat against temperatures that can plunge to -60 degrees Celsius at the equator during winter nights costs energy. Growing food under artificial lighting in pressurized greenhouses costs energy. Extracting water from subsurface ice costs energy. Processing the atmosphere to generate breathable oxygen costs energy. Communicating with Earth costs energy. Manufacturing replacement parts for broken equipment costs energy. And unlike Earth, where fossil fuels, hydroelectric power, wind, solar, and nuclear energy are all available at scale, Mars offers a much more limited menu. Solar power is possible on Mars, but considerably less effective than on Earth. Mars sits roughly 1.5 times farther from the Sun than Earth does, which means solar panels there receive about 43% of the solar energy available at Earth's surface, and that's before the dust storms we mentioned earlier start coating those panels and cutting output further. During a global dust storm, solar power generation can drop to near zero for weeks at a time. An outpost dependent entirely on solar power could face a catastrophic energy crisis with very little warning and very few options. Nuclear power is widely considered the most realistic solution. NASA and the Department of Energy demonstrated a small fission surface power system called kilopower, later developed into the more advanced Krusty reactor, that could potentially provide tens of kilowatts of continuous power to a small Mars outpost. In 2018, ground tests of this system were completed successfully at the Nevada National Security Site, demonstrating reliable sustained nuclear fission in a compact, space-qualified design. A handful of these reactors deployed around a habitat could provide stable baseline power independent of sunlight, dust conditions, or time of day. But nuclear technology brings its own complexities: shielding requirements, heat management, the political and regulatory landscape around launching fission reactors from Earth's surface. None of these are insurmountable problems, but all of them require careful engineering, and all of them add mass, cost, and risk to an already extraordinarily complex mission. And here is the deeper point. A permanent Mars settlement, one truly designed with no expectation of regular resupply from Earth, would need to achieve something that human civilization has never fully achieved even on our own planet: a closed, self-sustaining resource loop. Every molecule of water would need to be recaptured and recycled, every breath of air processed and returned, every calorie of food grown locally, every broken component either repaired or manufactured from available Martian materials. The engineering of that kind of closed-loop system, at the scale required to sustain even a small community of human beings, is arguably the most complex technological challenge our species has ever seriously contemplated. Let's talk about food. because this is one of those areas where the gap between what sounds plausible in a presentation and what is actually achievable in practice is genuinely sobering. Growing food on Mars is not simply a matter of bringing seeds and planting them in the soil. Martian regolith, the layer of loose rock and dust covering the surface, is not soil in any biological sense. It lacks the organic matter, the microbial ecosystems, and the nutrient availability that Earth plants depend on. It also contains perchlorates, chlorine-containing compounds that are toxic to most forms of Earth plant life and to humans. The concentration of perchlorates in Martian soil, confirmed by multiple landers and rovers, including the Phoenix lander in 2008, and verified repeatedly since, is high enough to pose a serious contamination risk to any food grown directly in unprocessed Martian material. This means food production on Mars would almost certainly rely on hydroponics or aeroponics, growing plants in carefully controlled nutrient solutions or misted environments, completely isolated from the Martian soil under artificial or supplemented lighting inside pressurized facilities. This is technically feasible. NASA and various research institutions have been running controlled environment agriculture experiments for decades. The veggie plant growth system aboard the International Space Station has successfully grown lettuce, kale, mizuna, and other leafy greens in microgravity. Astronauts have eaten fresh food they grew themselves in orbit. But scaling that technology from a modest experiment aboard a space station to a food production system capable of feeding a permanent colony, one where resupply missions are rare or non-existent, is an enormous leap. Caloric density matters, nutritional completeness matters, crop failure risk matters. A single fungal outbreak or equipment malfunction in a confined growing environment could devastate an entire food supply. Redundancy, diversity, and resilience would need to be engineered into every level of the agricultural system, and the energy cost of running those systems continuously would be substantial. Some researchers have pointed to certain fast-growing, nutrient-dense crops as particularly promising for Martian agriculture. Soybeans, sweet potatoes, wheat, and spirulina, a blue-green algae packed with protein and micronutrients, have all been identified as strong candidates, but no combination of crops currently tested can provide complete, long-term human nutrition in isolation without careful supplementation. The first Martian settlers would likely face nutritional challenges that compound slowly over years, manifesting as deficiencies in specific vitamins, minerals, and micronutrients that are difficult to replicate in a closed agricultural system. And then there is the psychological dimension of food, something that rarely makes it into the technical literature, but matters enormously in practice. Food is culture. Food is comfort. Food is one of the most powerful anchors of memory and identity that human beings possess. The astronauts who have participated in long-duration isolation studies consistently report that food, its variety, its flavor, its texture, the ritual of preparing and sharing a meal, becomes disproportionately important to morale over time. On a permanent Mars settlement, where the menu is constrained by what can be grown locally or what arrived in the last resupply years ago, the psychological weight of dietary monotony would accumulate steadily and relentlessly. Here is something that I think deserves to be said plainly, because it often gets lost in the excitement of mission announcements and rocket test flights. The people being asked to consider a one-way journey to Mars are not being asked to make a small sacrifice. They are being asked to give up everything that has ever defined human experience on this planet. They are being asked to trade the ocean for a desert, summer rain for a perchlorate-dusted plain, the warmth of physical human contact for a face on a screen, with a delay that makes real conversation nearly impossible. They are being asked to spend the rest of their lives in a suit or a pressurized room, eating food grown under fluorescent lighting, watching the sun rise as a slightly brighter star in a butterscotch sky. And some of them, when they understand all of this completely, clearly, and without romanticization, will still say yes. That tells us something profound, something that goes beyond Mars, beyond rockets, beyond the physics of orbital mechanics. It tells us something about the nature of meaning itself, about why human beings have always, in every era and every culture, been willing to walk into the unknown for something they believed in. The first people to cross the land bridge from Asia into the Americas did not know what was on the other side. The first Polynesian navigators to set out across the open Pacific in outrigger canoes, guided by stars and currents and the flight patterns of birds, had no map of what lay beyond the horizon. They went anyway, because the pull of the unknown and the desire to expand the boundaries of what is possible appears to be written somewhere very deep in who we are. Carl Sagan put it beautifully when he wrote about our species being at a point in history where, for the first time, we have the tools to become more than a single planet civilization. He saw in that possibility not just a practical hedge against extinction, important as that is, but a fulfillment of something essential in the human spirit. An answer to a question our ancestors asked every time they looked up at the stars and wondered whether something was out there. The first humans on Mars will carry that question with them. They will carry it across hundreds of millions of kilometers of empty space. And they may carry it to their graves in soil that has never known life, at least none that we have yet confirmed. But wait, that last phrase, none that we have yet confirmed, opens a door we haven't walked through yet. And behind that door is a question that completely reframes the moral stakes of everything we've been discussing. What if Mars is not, and has never been, lifeless? What if, buried beneath the surface, shielded from radiation by meters of rock, sustained by geothermal heat, surviving in pockets of liquid water in the deep subsurface, there are Martian microbes, ancient, alien, utterly unlike anything evolved on Earth? Because if that is true, and the scientific community has not ruled it out, then the arrival of human beings on Mars is not just an adventure story. It is a potential act of contamination on a cosmic scale. And whether those humans come back or not suddenly becomes a much smaller question than what they leave behind. Now we explore the possibility of life on Mars, what the evidence actually says, what missions like Perseverance are genuinely looking for, and what it would mean for humanity if we found it. Or, worse, if we destroyed it before we even knew it was there. Stay with me. This is where it gets truly extraordinary. If you are enjoying this journey, make sure to subscribe and give this video a like. In this channel, you get to stay connected to the universe's biggest stories, told as clearly and honestly as possible. Everything we've talked about so far exists within a framework that assumes one very specific thing. It assumes that Mars is a dead world, a barren, lifeless rock waiting patiently for us to arrive and make it interesting. But what if that assumption is wrong? What if Mars is not waiting for us at all? What if something is already there? This is not a casual question. It is arguably the most important scientific question in the entire field of astrobiology, the study of life's potential beyond Earth. And the answer, whatever it turns out to be, will fundamentally change the moral, philosophical, and practical calculus of every human Mars mission ever planned or imagined. Let's look at what the science actually says. Not the headlines, not the speculation. The evidence. Mars was not always the cold, dry, radiation-blasted world we see today. We know this with considerable confidence because the evidence is written into the planet's surface in extraordinary detail, and multiple generations of orbiters, landers, and rovers have been reading that evidence for decades. Roughly 3.5 to 4 billion years ago, during a period geologists call the Noachian era, Mars was a dramatically different place. The atmosphere was thicker, the climate was warmer, and liquid water flowed across the surface in quantities that would be recognizable to any of us. River valleys snaked across ancient highlands. Lakes filled enormous impact craters. There is compelling evidence, gathered in part by NASA's MAVEN orbiter, the Mars Atmosphere and Volatile Evolution mission, that Mars once had an ocean covering much of its northern hemisphere, potentially containing more water than the Arctic Ocean does today. That ancient ocean may have persisted for hundreds of millions of years. And on Earth, we know with certainty that life appeared in the oceans within roughly a few 100 million years of liquid water becoming stable on the surface. The oldest confirmed microbial fossils found on Earth date back approximately 3.5 billion years. Indirect chemical signatures suggest life may have been present even earlier, possibly as far back as 4 billion years ago, when the solar system was still young and chaotic, still being bombarded by asteroids and comets in a period called the Late Heavy Bombardment. Here is what makes this chronology so striking. The window during which Mars had liquid water on its surface overlaps almost precisely with the window during which life first appeared on Earth. Same solar system, same era, potentially the same conditions. And if chemistry organized itself into self-replicating molecules on one planet during that period, the question of why it couldn't have done the same on a neighboring planet, one that also had liquid water, energy gradients, and the raw chemical ingredients, becomes very hard to answer. This is the core of what scientists call the question of a second genesis. Did life arise independently on Mars? And if it did, is any of it still there? Now, here is where we need to be careful. Being careful with evidence is one of the things that makes science trustworthy, and it is one of the things that distinguishes it from wishful thinking. So let's be precise about what we know and what we don't. We have not found life on Mars, not confirmed life, not a single microbe, not a fossil, not an unambiguous biosignature. Every headline you may have seen suggesting otherwise has, upon careful examination, turned out to involve either misinterpretation, premature excitement, or evidence that has alternative non-biological explanations. The most famous example is ALH 84001, a meteorite found in Antarctica in 1984 that was later confirmed to have originated on Mars, blasted into space by an ancient asteroid impact, and eventually captured by Earth's gravity. In 1996, a team of NASA scientists led by David McKay published a paper in the journal Science claiming the meteorite contained potential evidence of ancient Martian life, including what appeared to be tiny fossilized structures resembling bacteria. The announcement was made at a White House press conference. President Bill Clinton addressed the nation. It was one of the most electrifying moments in the history of space science. And then the scientific community did what it does. It scrutinized the evidence rigorously from every angle, with increasing sophistication over the following years. The consensus that emerged, slowly, carefully, without drama, was that the structures in the meteorite, while genuinely interesting, could be explained by non-biological chemical processes. The case for life in ALH 84001 was not proven. Most astrobiologists today consider the question unresolved but lean toward non-biological explanations. This story is important not because it was a failure. It was a triumph of the scientific method. The system worked exactly as it should. A bold claim was made, rigorously tested, and found wanting, leaving the field wiser and more careful. But it also illustrates how desperately our pattern-seeking minds want to find life out there, and how carefully we need to guard against that desire, contaminating our interpretation of evidence. What we do have, and this is genuinely remarkable, is a growing body of evidence that Mars retains even today, conditions that might be compatible with certain forms of microbial life. In 2018, a team of Italian researchers analyzing radar data from the Marsis instrument aboard the European Space Agency's Mars Express orbiter reported evidence of a liquid water lake buried approximately 1.5 kilometers beneath the southern polar ice cap. The detection was based on radar reflectance signatures consistent with liquid water, possibly kept from freezing by a high concentration of dissolved salts, similar to subglacial lakes found beneath the ice sheets of Antarctica and Greenland on Earth. Those Antarctic subglacial lakes, Lake Vostok being the most famous, have been found to harbor microbial communities despite being sealed off from sunlight and the surface atmosphere for potentially millions of years. Subsequent analyses of additional Marsis data suggested the possible presence of multiple liquid water bodies in the same region, though some researchers have proposed alternative explanations involving clay minerals or other geological features that could produce similar radar signatures. The debate remains active and genuinely unresolved, but the possibility, the serious scientific possibility, of liquid water existing beneath the Martian surface today has not been ruled out. And where there is liquid water, there is at least the possibility of life. NASA's Curiosity rover has detected seasonal fluctuations in methane concentration in the Martian atmosphere. Methane is a molecule that breaks down relatively quickly under the bombardment of ultraviolet radiation, which means any methane present in the Martian atmosphere today must have been produced recently on geological timescales. On Earth, the vast majority of methane in the atmosphere is produced by biological processes, by microbes, by decomposing organic matter, by the digestive systems of animals. There are geological sources of methane too: volcanic activity, certain chemical reactions between water and certain types of rock in a process called serpentinization. But the seasonal variation Curiosity detected is intriguing because biological methane production tends to vary with temperature and chemical availability, both of which change with the Martian seasons. The Curiosity team, publishing in the journal Nature Geoscience in 2019, was extremely careful not to claim a biological explanation. The geological alternatives were presented fully and fairly, but the data is real, the seasonal pattern is real, and the scientific community has not yet settled on a definitive explanation. Curiosity's successor, the Perseverance rover, which landed in Jezero crater in February 2021, is carrying the most sophisticated suite of astrobiology instruments ever sent to another planet. Jezero crater was chosen specifically because it was once a lake fed by an ancient river delta, exactly the kind of environment where microbial life might have flourished billions of years ago and where biosignatures might be preserved in sedimentary rock. Perseverance has been drilling core samples from the crater floor and carefully sealing them in titanium tubes, leaving them on the surface to be collected by a future sample return mission. The Mars Sample Return Campaign, a joint project between NASA and the European Space Agency, is designed to bring those samples back to Earth, where they can be analyzed in laboratories with instruments far more powerful than anything that can currently be miniaturized and sent to Mars. If ancient biosignatures are present in those rocks, the technology needed to find them may well exist here on Earth. Waiting for the samples to arrive, the timeline for Mars sample return has faced significant budget pressures and schedule challenges in recent years. Independent review boards have raised concerns about cost overruns and the feasibility of the original architecture. The mission remains in development, but its future is subject to the political and financial realities of government space program funding, a reminder that even the most scientifically compelling projects exist in a deeply human context of budgets, priorities, and competing demands. Now, let's sit with the harder question. What if Perseverance finds something, not definitively, not dramatically, but a pattern in the chemistry of those rock cores that is, on balance, more consistent with biological processes than with purely geological ones, an isotopic ratio that looks like biological fractionation, an organic molecule in a configuration that chemistry alone would rarely produce. Something that makes the scientists in the laboratory look at each other very carefully across a very quiet room. What happens then? The implications cascade outward in every direction simultaneously. Scientifically, a confirmed second genesis, a second independent origin of life in the universe, would be perhaps the most transformative discovery in the history of human knowledge. It would not merely suggest that life exists beyond Earth. It would suggest that life is common, that in a universe of 2 trillion galaxies, each containing hundreds of billions of stars, the emergence of life from chemistry is not a miraculous accident, but a natural consequence of the right conditions. It would make the universe suddenly, overwhelmingly alive, at least in principle. Philosophically and theologically, the reverberations would take generations to fully process. Every tradition that places human beings or Earth life at the center of a special cosmic narrative would be confronted with evidence that the universe had already done this somewhere else, independently, long before humans existed to ask the question. And practically, for the Mars missions we have been discussing throughout this entire video, it would create an immediate and profound ethical crisis. Because here is the problem with sending humans to Mars if Mars might harbor life. Human beings are, in the most literal biological sense, walking contamination events. Your body contains approximately 38 trillion microbial cells, bacteria, archaea, fungi, viruses, that are as much a part of you as your own human cells. Every surface you touch, every breath you exhale, every flake of skin you shed is a potential vector for introducing Earth biology into a Martian environment. Spacecraft are sterilized to extraordinary standards. NASA's Office of Planetary Protection maintains protocols requiring that spacecraft sent to potentially habitable environments carry fewer than 300,000 bacterial spores on their entire exterior surface. But no protocol designed for a robotic spacecraft can be applied to a human being. A human crew is, by definition, a biological payload that cannot be sterilized. The consequence is stark. If humans land on Mars before we have definitively determined whether Mars is or ever was inhabited, we may permanently compromise our ability to answer that question. Martian microbes, if they exist, could be overwhelmed or fundamentally altered by the torrent of Earth biology arriving with the crew. Or worse, Earth microbes carried by the crew might thrive in Martian niches, evolving rapidly in a new environment, and be mistaken for indigenous Martian life by future researchers. The Office of Planetary Protection exists precisely to grapple with these concerns. But its protocols were designed in an era when human Mars missions were theoretical. As they become practical, the tension between the imperative to explore and the imperative to preserve potential scientific evidence of extraterrestrial life is becoming one of the most urgent ethical debates in all of science. Some researchers have proposed that robotic exploration should precede human landing by enough time and with enough coverage to definitively settle the question of extant Martian life before any human boot touches the surface. Others argue that the very limitations of robotic systems mean certain answers can only be obtained by human researchers in the field, and that delaying human exploration indefinitely in pursuit of certainty we may never achieve is itself a form of failure. There is no clean answer, and whoever makes the final call, a space agency director, a national government, a private company, will be making a decision with consequences that extend far beyond any individual mission or generation. Let's pull back for just a moment and look at the full picture we've assembled so far, because it is worth appreciating how many dimensions this single question Will the first humans on Mars come back? Has turned out to have. We've talked about the physics of interplanetary travel, the brutal mathematics of propellant and orbital mechanics. We've talked about what radiation does to the human body over years of exposure without a planetary magnetic field to provide shelter. We've talked about bone density and cardiovascular decline, and the slow physiological unraveling that microgravity and low gravity impose on a body built for Earth. We've talked about the psychology of extreme isolation and the human need for connection and meaning, and the kind of inner landscape required to survive a one-way journey with grace. We've talked about children born on Mars who may never be able to return to a planet they have never seen. We've talked about energy and food, and the extraordinary engineering challenge of a closed-loop, self-sustaining habitat. And now we've talked about the possibility that Mars may not be lifeless, and what that would mean for everything. Each of these layers adds complexity. Each of them adds weight. And together, they paint a portrait of a mission so demanding, so consequential, and so irreversible that it stands apart from every other journey human beings have ever undertaken. And yet, the conversations are happening. The rockets are being built. The rovers are collecting samples. The scientists are analyzing data in laboratories on multiple continents. The trajectory of human civilization is bending, however slowly and unevenly, toward that pale red dot in the night sky. Let's ask the uncomfortable question, why Mars? Not rhetorically, not as a setup for an obvious answer. Genuinely, why this particular planet at this particular moment with this particular level of urgency? Because when you step back from the excitement of rocket launches and rover landings and look at the full picture with clear eyes, the choice of Mars as humanity's next home is not as self-evident as it might seem. It is a decision shaped by physics, yes, but also by history, by culture, by ego, by fear, and by a set of assumptions about our future that deserve to be examined rather than simply inherited. To understand why Mars specifically, you first have to understand the argument that drives the entire conversation. The argument is not primarily about scientific curiosity, though that is real and valuable. It is not primarily about resources, though those conversations exist too. The core argument, the one that gives the whole enterprise its sense of moral urgency, is about survival. The argument goes like this: Earth is not a safe long-term address for our civilization. Over sufficiently long timescales, the planet faces existential threats that no amount of technology or political will applied solely on Earth can fully neutralize, and therefore becoming a multi-planetary species is not an optional aspiration. It is a biological and civilizational imperative. That argument is made by serious people. Elon Musk makes it constantly. Stephen Hawking made it repeatedly in the years before his death, warning that humanity's long-term survival depends on establishing colonies beyond Earth within the next few centuries. The logic has a certain undeniable force. Let's take it seriously and trace it all the way through. What are the actual existential threats to life on Earth? Let's go through them honestly, with real numbers and real timescales, because the details matter enormously when we're using them to justify the most expensive and dangerous undertaking in human history. The first category is asteroid and comet impacts. This is the most cinematically familiar threat, and it is real. The impact that ended the reign of non-avian dinosaurs 66 million years ago released energy estimated at roughly 1 billion times that of the atomic bombs dropped on Hiroshima and Nagasaki. It triggered wildfires, a global winter caused by debris blocking sunlight, acid rain, and a collapse of food chains that killed approximately 75% of all species on Earth. An event of that magnitude would almost certainly end human civilization as we know it. But here is the critical detail. Events of that magnitude are extraordinarily rare. The object that caused the Cretaceous Palagine extinction was roughly 10 kilometers across. Impacts from objects that size occur on timescales of roughly 100 million years. NASA's Planetary Defense Coordination Office, along with partner agencies around the world, has now catalogued the vast majority of near-Earth objects larger than 1 kilometer in diameter, and none of the known ones pose a significant threat to Earth in the foreseeable future. For smaller but still civilization-threatening impactors, in the range of 100 meters to 1 kilometer, detection and tracking is ongoing, and deflection technologies like the DART mission, which successfully altered the orbit of the asteroid Dimorphos in September 2022, demonstrate that we are developing real tools to address this threat without needing to leave the planet. The second category is supernovae. A nearby stellar explosion could theoretically irradiate Earth's atmosphere, strip away the ozone layer, and expose the surface to lethal doses of radiation. This is a genuine astrophysical phenomenon. There is evidence in the geological record, including in deep-sea sediment cores containing unusual concentrations of iron-60, a radioactive isotope produced by supernovae, that Earth has experienced elevated cosmic ray flux from nearby stellar explosions in the past. But the nearest stars capable of going supernova in the astronomically near future, candidates like Betelgeuse and Eta Carinae, are hundreds to thousands of light-years away. The lethal radius of a supernova for complex surface life is generally estimated at around 25 to 50 light-years. No known supernova candidate sits within that range of Earth. The timescale for a genuinely threatening nearby supernova is, by current assessments, extraordinarily long, hundreds of millions to billions of years. The third category is what is sometimes called anthropogenic risks. Threats we create ourselves: climate change, nuclear war, engineered pandemics, the potential misalignment of artificial intelligence systems, the breakdown of global cooperation and institutions. These are real, they are urgent, and they are happening on timescales of decades to centuries rather than millions of years. And here is where something important needs to be said plainly. A Mars colony does not solve any of these problems. A Mars colony in 2050 or 2100 or 2200 would be an extraordinarily fragile outpost, a few hundred people at most, entirely dependent on a continuous supply chain from Earth for critical components, medicines, and technologies they cannot yet manufacture locally. If Earth were struck by a civilization-ending catastrophe tomorrow, that Mars outpost would not survive the loss of the industrial civilization supporting it. Not for long, certainly not for generations. The idea of Mars as a backup drive for human civilization, a place where the species continues even if Earth fails, requires a Mars settlement of a scale and self-sufficiency that is not achievable in any realistic near-term timeframe. It requires a city of potentially millions of people with a fully independent industrial base, a complete technological ecosystem, and generational continuity. That is not a reason to abandon the vision. It is a reason to be honest about the timeline and to avoid letting the urgency of the survival narrative be used to justify cutting corners on the ethical, biological, and planetary protection concerns we've already discussed. So if the immediate survival argument is weaker than it sounds at first, why Mars and why now? The honest answer has several components. One is opportunity. The technologies required for crewed Mars exploration, reusable heavy-lift rockets, advanced life support systems, in-situ resource utilization, have matured more in the last 15 years than in the previous 40. The convergence of private investment, computational advances, and lessons learned from decades of robotic Mars exploration has created a window of genuine feasibility that did not exist in the era of Apollo. Another is inspiration. There is a deep and legitimate argument that humanity needs a shared, positive, forward-looking vision of the future. Something that transcends national boundaries and political divisions and reminds us of our capacity for extraordinary collective achievement. The Apollo program did something to the human spirit that went far beyond the scientific value of the moon rocks brought back. It demonstrated, at a moment of profound political tension, that human beings could do the impossible. A crewed Mars mission or a permanent Mars settlement could carry similar cultural power, perhaps more. And a third reason is something harder to articulate but no less real. It is the pull of the horizon itself, the same drive that sent those first Polynesian navigators out into the open Pacific, the same impulse that made early humans walk out of Africa and keep walking until they had populated every habitable corner of the planet. There is something in us, something that predates civilization and language and written history, that tilts toward the unknown, and Mars is the most knowable unknown in our immediate cosmic neighborhood. It is close enough to reach with current technology, it is understood well enough to plan for, and it is alien enough to represent a genuine frontier. None of these reasons require us to pretend the risks are smaller than they are. None of them require us to avoid the uncomfortable truth that the first humans who go may never come back. In fact, I would argue that the mission is more meaningful, not less, when we look at it without flinching, when we see it whole, the radiation and the bone loss and the isolation and the one-way mathematics and the possibility of Martian life and the enormous ethical questions and the physiological divergence of future generations, and still say, yes, this is worth doing. That is not naivety. That is a particular kind of courage that belongs to the long tradition of human exploration at its finest. But I want to push the question even further, because asking why Mars specifically opens a door to a much larger question that cosmologists and planetary scientists are genuinely grappling with right now. Are there better options? In our own solar system, the most scientifically compelling locations for life are not Mars. They are the ocean worlds. Europa, the fourth largest of Jupiter's moons, has a global ocean of liquid salt water beneath an icy crust, potentially containing twice as much water as all of Earth's oceans combined. That ocean is kept liquid by tidal forces as Europa is constantly flexed by Jupiter's immense gravitational pull. Where there is liquid water, energy gradients, and chemical complexity, on Earth there is always life. Europa's ocean may have been liquid for billions of years. NASA's Europa Clipper mission, launched in October 2024, is currently en route to conduct detailed flybys of Europa beginning in 2030, specifically designed to assess its habitability. Enceladus, a small moon of Saturn, actively vents water vapor and ice particles from its subsurface ocean through geysers near its south pole. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, before being deliberately plunged into the planet's atmosphere, flew directly through those plumes and detected water, sodium, silica particles, carbon dioxide, methane, molecular hydrogen, and complex organic molecules. Molecular hydrogen in particular is significant. It suggests active hydrothermal chemistry on the ocean floor, the same type of environment where some scientists believe life first emerged on Earth around deep-sea hydrothermal vents. Titan, Saturn's largest moon, has a thick nitrogen-rich atmosphere and lakes and rivers of liquid methane and ethane on its surface. It is the only other world in the solar system besides Earth with stable surface liquids. NASA's Dragonfly mission, a rotorcraft lander designed to fly between different sites on Titan's surface, is scheduled for launch in 2028 and arrival at Titan in the early 2040s. The chemistry of Titan's atmosphere, which produces complex organic molecules called tholins through interactions with sunlight and energetic particles from Saturn's magnetosphere, is thought to resemble the chemistry of early Earth before life emerged. None of these destinations are realistically accessible to human beings with near-term technology. Europa's proximity to Jupiter exposes any visitor to radiation doses that would be lethal in a matter of days without extraordinary shielding. Enceladus and Titan are nearly 1.5 billion kilometers from Earth, roughly 10 times farther than Mars. The travel times, energy requirements, and life support challenges dwarf even those of a Mars mission. For the foreseeable future, these worlds will be explored by robotic spacecraft, with humans watching from afar. Mars is the destination for human exploration, not because it is the most scientifically interesting target in the solar system, but because it is the most reachable. It sits at a distance and in an orbital configuration that makes crewed missions conceivable with technology we either already have or can credibly develop in the near term. In the hierarchy of priorities driving the Mars push, accessibility ranks very high, perhaps higher than most people realize. Now I want to bring in something that reframes the entire conversation in a way that I find genuinely humbling. It is called the Fermi paradox, and if you haven't encountered it before, hold on, because it is one of the most disturbing ideas in all of science. The Fermi paradox begins with a straightforward observation made by physicist Enrico Fermi during a lunch conversation at Los Alamos in 1950. The universe is approximately 13.8 billion years old. It contains an estimated 2 trillion galaxies, each containing hundreds of billions of stars. Many of those stars are billions of years older than our Sun. Many of them have planets. Around many of those planets, the conditions for life as we understand it may well exist or may have existed for billions of years longer than Earth has. Given all of that, given the sheer age and scale of the universe, and given that even a civilization modestly more advanced than ours could spread across an entire galaxy in a cosmologically brief span of time, using technologies we can at least theoretically envision, the galaxy should, by many estimates, be teeming with evidence of intelligent life, radio signals, megastructures, the signatures of stellar engineering, something. And yet, we have heard nothing, seen nothing, detected nothing unambiguous. The silence is total. And that silence, that vast, eerie cosmic silence, is the Fermi paradox. Where is everybody? There are many proposed solutions, and they range from mildly reassuring to deeply alarming. Perhaps intelligent life is genuinely rare. Perhaps the chain of improbable steps required to go from chemistry to microbes to multicellular life to intelligence to technological civilization is so unlikely that we may be among the first to achieve it, or even the only ones. Perhaps intelligent civilizations tend to destroy themselves before achieving the capacity for interstellar communication or travel through war, environmental collapse, or the misuse of their own technologies. Perhaps the universe is full of life and intelligence, but the distances and timescales involved make detection essentially impossible with any technology we can imagine. Perhaps we are not looking in the right way, or at the right frequencies, or with the right assumptions, or, and this is the one that keeps certain cosmologists awake at night, perhaps there is something called the Great Filter, a step in the development of life or civilization that is so extraordinarily difficult to cross that virtually no species ever gets past it. The terrifying version of this idea is that the Great Filter lies ahead of us, not behind us, that we have not yet encountered the thing that stops civilizations, that the silence of the cosmos is not evidence of rarity, but of a universal ceiling that no civilization has yet managed to break through. If that is true, if the Great Filter is real and it lies ahead, then the urgency of becoming multiplanetary takes on a completely different character, not as insurance against asteroid impacts or climate change, but as a race against something we don't yet understand and may not see coming until it is very close. This is speculative, deeply speculative. But it is the kind of speculation that serious scientists and philosophers take seriously, because the alternative, assuming the silence means nothing and the future is open, may be dangerously complacent. Now pull all of this together, the opportunity created by maturing technology, the inspiration that a shared human frontier provides, the pull of the horizon that is woven into our nature as a species, the possibility, however speculative, that the window for becoming multiplanetary may not stay open indefinitely, and then place inside that context the individual human being, the person, real, flawed, mortal, homesick before they even leave, who raises their hand and says yes, who goes through the medical screening and the psychological assessment, and the years of training and the goodbyes that feel like endings, because they are, who straps themselves into a capsule on top of a controlled explosion and watches Earth shrink behind them into a pale blue marble, and then a bright star, and then nothing visible at all. That person is carrying something on behalf of all of us, something that is not fully articulable but is fully real. They are carrying the question that every human being who has ever looked up at the night sky has felt in some form: what is out there? And they are walking directly into it. Whether they come back or not, what they find and what they build and what they endure will echo forward through human history in ways we cannot yet measure or predict. Just as we cannot fully measure the courage of the first person to cross an ocean or walk onto a continent no human had ever stood on, or look through a telescope and understand for the first time that the stars are not lanterns hung from a fixed dome but suns, some of them far larger and older than our own, scattered across an incomprehensible depth of space. We are made of that history, and the first human beings on Mars will be made of us. Let's talk about the moment itself, not the press conference, not the launch broadcast, not the carefully edited highlight reel that will play on screens around the world. The actual moment, the one that happens before the cameras can fully process what they're seeing, before the mission controllers in Houston or Pasadena, or wherever the command center happens to be, have time to exhale, the moment the first crewed spacecraft enters the Martian atmosphere. Because that moment, that specific, irreversible, terrifying, magnificent sequence of events, is one of the most dangerous things any human being has ever attempted. And understanding exactly why tells you something essential about the entire mission. About the knife edge between success and catastrophe that the crew will be riding from the very first second they commit to entry. Here is what happens. The spacecraft approaches Mars at roughly 24,000 kilometers per hour. At that speed, the thin Martian atmosphere, less than 1% the density of Earth's at sea level, is not gentle. It is a wall of compressed, superheated gas that forms in front of the vehicle as it plunges downward. Temperatures on the heat shield can reach values comparable to the surface of the sun. The communications blackout that results from the plasma sheath surrounding the vehicle cuts the crew off from Earth completely, for somewhere between 10 and 20 minutes, depending on the trajectory. Mission controllers can do nothing. The crew can do nothing that the automated systems haven't already been programmed to do. They are passengers in the most violent deceleration event of their lives, inside a vehicle being tested against conditions that no ground simulation can fully replicate. This is the phase NASA engineers famously call the 7 minutes of terror, the approximate time from atmospheric entry to surface touchdown for a robotic lander. For a crewed vehicle, which is necessarily heavier and more complex, the sequence is longer and the engineering challenge is substantially greater. In fact, the problem of landing a human-rated spacecraft on Mars, heavy enough to carry people, supplies, and return propellant, is one of the most technically demanding unsolved problems in the entire Mars mission architecture. Here's why. Mars sits in an awkward middle ground. Its atmosphere is thick enough to make a purely propulsive landing like touching down on the moon, prohibitively fuel expensive, but it is too thin to allow parachutes alone to slow a heavy vehicle to a safe landing speed. The combination of heat shield, supersonic parachute deployment, and powered descent that worked for the Curiosity and Perseverance rovers, each weighing roughly 1 metric ton, cannot simply be scaled up for a crewed lander that might weigh 20, 40, or even 100 metric tons fully loaded. The physics don't cooperate. New technologies are needed, technologies that have never been tested in the actual Martian environment at full scale. SpaceX's proposed solution with Starship is an aerodynamic entry profile combined with propulsive landing, using the vehicle's body for initial deceleration and then flipping to a vertical orientation and firing engines to land upright. This approach has been demonstrated on Earth during Starship test flights. But the Martian atmosphere presents different density gradients, different wind patterns at different altitudes, and a surface gravity field that requires precise engine throttling calibration. The margin between a successful landing and a catastrophic impact at those speeds and in that environment is extraordinarily narrow, and the crew will have felt all of this in their bodies. After 6 to 9 months in transit, during which their cardiovascular systems weakened, their bones thinned, their spatial orientation systems adapted to weightlessness, they will suddenly be subjected to the crushing forces of atmospheric entry deceleration. The G-forces during this phase can reach several times the pull of Earth's gravity, sustained over minutes. For a body that has spent the better part of a year in near weightlessness, that is a profound physiological shock. Astronauts returning from the International Space Station after 6 months in orbit are, as we discussed earlier, carried from their capsules. The Mars crew will have been in space significantly longer, and they will need to function, they will need to monitor systems, make decisions, respond to anomalies, and potentially intervene manually if the automated systems encounter something outside their programming. This is the reality of those first minutes on Mars that the mission architects spend long nights working through. Assume the landing goes perfectly, the vehicle settles onto the surface, the dust plume disperses, the engines fall silent. What happens next? The crew does not step outside, not for hours, possibly not for days. First, every system on the lander has to be checked, cross-checked, and verified. The habitat module, whether it arrived separately in advance or is part of the landing vehicle itself, needs to be confirmed intact and pressurized. Life support systems need to be running and stable. Power generation, whether solar or nuclear, needs to be confirmed operational. Communications with Earth need to be re-established after the entry blackout, and the surface dust environment needs to be assessed. Planetary protection protocols require that the crew minimize their biological footprint on the Martian surface. Every excursion outside the habitat, every suited EVA or extravehicular activity is a potential contamination event. The suits themselves, however carefully maintained, carry microbial passengers. The airlocks that transition between the pressurized interior and the Martian environment are one of the most critical engineering components in the entire habitat design. A failure there, a seal breach, a pressure differential anomaly, a mechanical jam at the wrong moment could be fatal within minutes. The suits the crew wears outside are extraordinarily complex machines. They maintain internal pressure against the near vacuum of the Martian atmosphere. They regulate temperature against swings that can range from -80 degrees Celsius at night to perhaps +20 at midday near the equator. They provide breathable oxygen. They shield against radiation. They allow movement, enough movement to work, to collect samples, to operate equipment, while maintaining all of those functions simultaneously. A modern spacesuit is arguably the most sophisticated piece of personal equipment ever built. and it exists at the intersection of about a dozen different engineering disciplines. Spacesuit failures have caused emergencies in low Earth orbit. On Mars, with no rescue possible and a communication delay of up to 22 minutes, a suit emergency is a genuine life-or-death situation resolved entirely by the crew themselves. The first EVA, the first time a human being steps out onto the Martian surface, will be one of the most carefully choreographed sequences of events in the history of exploration. Every step will have been rehearsed hundreds of times in analog environments on Earth, in virtual reality simulations, in pressure chambers and suit labs, and it will still feel like nothing any training could have fully prepared them for, because the moment a human being stands on the surface of Mars and looks around, really looks, with biological eyes adapted by millions of years of evolution to the light and color palette of Earth, they will see something no human nervous system has ever processed before. A landscape that is simultaneously familiar and utterly alien, rock, sky, horizon, and yet wrong in ways that are impossible to fully describe in advance. The colors slightly off, the shadows slightly too sharp in that thin air, the sky that extraordinary dusty pink that no sunset on Earth quite matches, the horizon slightly closer than expected. Mars is a smaller planet with a radius of roughly 3,390 kilometers compared to Earth's 6,371, and on flat terrain, the curvature brings the horizon noticeably nearer. And the silence, an almost total silence, because the thin atmosphere transmits sound very poorly. A shout on Mars would carry roughly 40% less far than the same shout on Earth, muffled and attenuated by that wisp of carbon dioxide. The crew will hear their own breathing inside their helmets, their own heartbeat, and beyond that, depending on whether the wind is still, almost nothing. That silence is the sound of 4.5 billion years of geological time, uninterrupted by the voice of any living thing, at least any living thing we know of yet. Now let's talk about what goes wrong, because in the history of human spaceflight, something has always gone wrong. Every single crewed mission in the history of the space age has encountered anomalies, equipment failures, unexpected conditions, or moments of genuine crisis. Many of those crises were managed brilliantly and resulted in no loss of life. Some were not. Apollo 1, Soyuz 1, Soyuz 11, Challenger, Columbia. Each of these events killed people. Each happened despite extraordinary engineering, extensive testing, and the most capable teams in the history of aerospace. The difference on Mars is the isolation. On every crewed mission in the history of spaceflight, until this moment, Earth was close. Rescue, or at least guidance and support, was minutes away at most. Apollo 13, perhaps the most celebrated crisis management achievement in space history, saw the crew survive a catastrophic oxygen tank explosion because the engineering teams on the ground had 3 days to work the problem. Real-time communication allowed constant back and forth, and the vehicle was close enough to Earth that a lunar trajectory abort was possible. Even so, it was extraordinarily close. Jim Lovell, Jack Swigert, and Fred Hayes returned to Earth in a damaged spacecraft with failing power systems, inadequate heating, and a CO2 scrubber improvised from spare parts guided by instructions radioed up from Earth in real time. On Mars, none of those lifelines exist. The communication delay alone makes real-time crisis support from Earth impossible. A fire in the habitat, which in a pressurized oxygen-enriched environment can spread with devastating speed, has to be dealt with by the crew right now with whatever tools and training and presence of mind they can bring to bear in that moment. A medical emergency, a stroke, a burst appendix, a severe injury from a suit breach or equipment failure has to be managed by crew members who are trained as emergency medical technicians but are not surgeons, in a medical bay that is stocked and capable but is not a hospital, with no possibility of evacuation to a higher level of care. The mission architecture has to account for this reality explicitly, and the most sobering versions of that accounting lead to a conclusion that mission planners prefer not to dwell on in public. Some failure modes on Mars have no survival path. A catastrophic hull breach in the main habitat. A complete failure of the power generation system during a prolonged dust storm. A fire that spreads faster than suppression systems can manage. A medical condition that progresses beyond the crew's treatment capabilities. These are low-probability events. The engineering is designed to make them as unlikely as possible, with redundant systems and fail-safe designs and extensive failure mode analysis. But low probability over a multi-year mission involving complex systems in a novel and hostile environment is not zero probability. It is never zero. The people who design Mars missions know this. The people who will fly those missions know this. And the people who will be left on Earth, the families, the colleagues, the mission controllers watching data streams that are 22 minutes out of date, know this too. It is the knowledge that sits quietly beneath every celebration, every milestone, every successful test. The knowledge that this is genuinely dangerous in a way that most human activities in the modern world are not. Now here is something that rarely gets discussed in the mainstream narrative around Mars exploration. Something that the engineering documents acknowledge but the press releases do not emphasize: the plan for what happens if someone dies on Mars. It is not a morbid hypothetical. It is a mission requirement. A Mars crew of 4 to 8 people living in close quarters for years will face the statistical reality of human mortality. Even in a young, healthy, carefully selected population, acute medical events can occur. And if one does, if a crew member dies on Mars, the mission must continue, because there is no going home early, there is no grief sabbatical. There is no ceremony on Earth attended by the people who knew them best. At least not one the surviving crew members can attend. Mission designers think carefully about the psychological protocols for this scenario, about the importance of ritual, about how the remaining crew processes loss while continuing to function at the high level the mission demands, about the physical reality of what happens to a human body in a pressurized habitat or outside one, on a world with no established burial tradition, no soil microbiome to facilitate decomposition, in the way Earth soil would, no framework of cultural practice to draw on. These are not comfortable thoughts, they are honest ones. And the people who choose to go on this mission, if and when it happens, will have thought about them more deeply than most of us ever will. That level of deliberate confrontation with mortality, that willingness to look at the full truth of what they are walking into and choose to go anyway, is something I find genuinely extraordinary. Not heroic in the simple, uncomplicated sense that word sometimes implies. Something more complex than that. Something that sits at the intersection of courage and purpose, and a particular relationship with the finite nature of a human life that most of us never have to fully reckon with. Let's bring in something concrete. Something being built and tested right now that directly addresses several of the survival challenges we've been discussing. NASA's Artemis program, designed to return humans to the Moon as a proving ground for Mars, is developing a series of technologies specifically intended to address the gap between what we currently know how to do and what a Mars mission requires. The Lunar Gateway, a small space station planned for lunar orbit, will serve as a testbed for long-duration deep space life support systems. The advanced spacesuit systems being developed for Artemis, the XEMU suit, incorporate lessons from decades of EVA experience on the International Space Station and are being designed to be more flexible, more capable, and more reliable than anything previously flown. The Moon in this framing is not the destination. It is the classroom. Every hour of EVA experience accumulated on the lunar surface Every failure mode discovered and corrected in a lunar habitat, every medical protocol tested in a deep space environment that is close enough for emergency return but far enough to impose genuine operational constraints, all of it feeds directly into the Mars mission design database. The Moon is approximately 3 days away from Earth at current travel speeds. Mars is 6 to 9 months. The Moon gives us a chance to learn the hard lessons in a neighborhood where rescue is at least theoretically possible before we step out into the deep ocean of interplanetary space where it is not. This is the logic of the Moon to Mars approach, and it is genuinely sound. The frustration expressed by some in the space advocacy community, the sense that the Moon is a detour from the real destination, misses the point. The Moon is not a detour. It is an essential bridge between where we are and where we need to be. The gap in capability between a 6-month stay on the International Space Station in low Earth orbit and a 3-year crewed mission to Mars's surface is not a gap that can be jumped in a single bound. But there is a tension at the heart of all of this that I want to name clearly, because it runs through every aspect of the Mars mission conversation and affects how we should think about the question of whether the first crew comes back. The tension is between urgency and readiness. The urgency argument says the longer we wait, the more opportunities we miss. Launch windows open every 26 months. The geopolitical landscape shifts. Funding ebbs and flows with political cycles. The engineers and scientists who carry the deepest institutional knowledge of how to do this are aging. The technologies being developed by private companies are moving fast, and the competitive dynamics of the space industry may create pressures to launch before full readiness is achieved. In that environment, waiting for perfection may mean waiting forever. The readiness argument says the consequences of sending humans to Mars before the technology, the medicine, the psychology, and the mission architecture are genuinely ready are not the consequences of a delayed schedule or a missed budget target. They are the consequences measured in human lives, in irreversible decisions made on behalf of people who trusted the system that selected and trained and launched them, in potential contamination of a scientifically irreplaceable environment. These consequences cannot be walked back. They cannot be patched in the next software update. Both arguments are serious, both deserve respect, and the resolution, if there is one, lives not in choosing one over the other, but in being ruthlessly honest about which specific gaps are truly acceptable and which are not, in maintaining the kind of institutional culture that allows engineers and physicians and psychologists to raise concerns without political pressure to suppress them, the kind of culture that, frankly, did not always exist in the programs that produced Challenger and Columbia. The philosopher and astronomer Carl Sagan used to say that the universe is not obliged to make sense to us, that it does not care about our comfort or our schedules. But he also believed deeply, visibly, in every word he wrote, that the act of reaching toward understanding, of sending fragile human beings across the darkness to stand on alien ground and ask questions the answers to which will change everything, that this act is one of the most meaningful things our species has ever done. He was right. And the people who go to Mars will carry that meaning with them, whether they come back or not. If you are still watching, it means you feel that pull toward the big questions, the deep answers, and the real scale of things. Make sure to subscribe and give this video a like. Every video this channel exists to feed exactly that part of you. Let me ask you something that might sound like it belongs in a history class, rather than a video about space exploration. What turns a settlement into a nation? It's a question humanity has answered before, not cleanly, not without conflict, not without blood, but answered. The American colonies, the Australian settlements, the gradual, painful, often violent process by which distant outposts of empire became sovereign entities with their own laws, their own identities, their own relationship with the land they occupied. Every time it happened, the people back home were surprised. Every time, the people who had actually lived through the hardship of building something from nothing in an alien environment felt that the surprise itself was the most revealing thing of all. Because when you are the one who survived the crossing, who built the shelter, who figured out how to eat and stay warm and keep your community together through the first catastrophic winter, the idea that someone thousands of kilometers away, who has never seen your sky or breathed your air or buried your dead, still gets to tell you how to live becomes increasingly difficult to accept. Now multiply that distance by 10,000. Add a communication delay that makes real-time governance literally impossible. Add the fact that the people on that distant settlement cannot physically leave, even if they wanted to, cannot attend a hearing, cannot appeal to a court in person, cannot vote in an election whose outcome they have to live with, but had almost no practical ability to influence. Welcome to the political future of Mars. And it is arriving faster than almost anyone in mainstream political discourse has noticed. Let's start with the legal foundation, because it matters enormously and it is already showing serious cracks. The bedrock of international space law is the Outer Space Treaty of 1967, negotiated at the height of the Cold War, signed initially by the United States, the Soviet Union and the United Kingdom, and subsequently ratified by over 110 nations. The treaty establishes several principles that were visionary for their time and are increasingly strained by the realities of the 21st century space economy. The treaty states that outer space, including the moon and other celestial bodies, is the province of all mankind. It cannot be claimed by any nation through sovereignty, use, or occupation. No flag planted on Mars by any country or company conveys territorial ownership. No nation can declare Mars or any part of it its sovereign territory. It also establishes that nations are responsible for the activities of their nationals in space, including private companies operating under their jurisdiction, and it requires that states avoid harmful contamination of celestial bodies and adverse changes to the environment of Earth resulting from the introduction of extraterrestrial matter. For 1967, these principles were remarkably forward-thinking. They prevented the extension of the Cold War's territorial competition into space in the most dangerous possible form. They established a framework of shared responsibility that has, broadly speaking, held together for nearly 6 decades. But they were written for a world in which space activity meant government agencies launching robotic probes and, eventually, a handful of government astronauts on carefully defined missions. They were not written for a world in which a private company is seriously planning to establish a permanent settlement of potentially thousands of people on Mars under its own operational control, using resources extracted from the Martian surface to build a self-sustaining economic system. The Outer Space Treaty says nations cannot claim sovereignty over Mars. It says nothing coherent about what happens when a private city on Mars decides it no longer recognizes the authority of any nation on Earth. This is not an abstract hypothetical. It is a scenario that Elon Musk has explicitly and publicly discussed. In interviews and in the terms of service documents for Starlink, SpaceX's satellite internet service, language appeared acknowledging that for services provided on Mars, the parties recognize Mars as a free planet and agree that disputes will be settled through principles of self-governance rather than Earth law. Legal scholars noted immediately that this was a company unilaterally asserting that its Mars operations would be governed by rules it set itself rather than by any existing international framework. The Starlink terms of service do not have the force of international law, but the intention behind them is revealing. SpaceX's internal planning documents and Musk's public statements have consistently described the goal as a self-governing Mars city, one that starts under Earth authority out of practical necessity, but is explicitly designed to transition to independence as it becomes self-sufficient. The analogy drawn is historical. Early colonial settlements were dependent on their home nations for supplies, protection, and governance. As they grew in population and capability, that dependence diminished, and the political relationship evolved, sometimes peacefully, more often not. The question of who governs a permanent Mars settlement is not merely philosophical. It has immediate practical consequences for every aspect of life there. Who decides how limited resources, water, power, food, habitat space, are allocated during a shortage? Who adjudicates disputes between settlers? What constitutes a crime on Mars, and what is the appropriate response to it, given that the conventional tools of law enforcement, courts, detention facilities, the possibility of deportation, all function very differently in a sealed habitat where expulsion from the community is effectively a death sentence? What rights do individual settlers have against the authority, whether a space agency, a private company, or a nascent governing body, that controls the life support systems they depend on for survival? These questions do not have answers yet. The legal scholarship addressing them is growing but is far from settled, and the political will among Earth's nations to negotiate a new, updated framework for space governance, one that actually addresses the realities of permanent human settlement rather than government-sponsored exploration, has been weak to essentially non-existent. The Artemis Accords, a series of bilateral agreements initiated by the United States in 2020 and now signed by over 40 nations, represent an attempt to build a practical framework for lunar and eventually Martian activities. They address issues like the registration of space objects, the sharing of scientific data, and the concept of safety zones around operational facilities. They introduce the idea of resource extraction rights, allowing nations and companies to own resources they extract from celestial bodies, even if they cannot own the territory itself. This is a significant departure from the strictest reading of the Outer Space Treaty and has been criticized by Russia and China, who are not signatories, as an attempt by the United States to unilaterally rewrite the rules of space governance in ways that favor American commercial interests. The geopolitics of space, which for decades played out primarily as a competition between the United States and the Soviet Union, has become genuinely multipolar in ways that create new risks and new complexities. China's space program has achieved remarkable milestones in recent years. The Chang'e series of lunar missions has landed rovers and returned samples from the Moon. The Tianwen-1 mission successfully placed a rover on Mars in 2021, making China only the second nation, after the United States, to successfully operate a rover on the Martian surface. China has announced ambitions for crewed lunar missions and eventually human Mars exploration. Russia, despite the significant setbacks its space program has experienced in recent years, remains a significant actor. India's space program, which successfully placed the Chandrayaan-3 lander near the lunar South Pole in 2023, a globally historic first, is growing rapidly in ambition and capability. A permanent human settlement on Mars, established in this multipolar landscape, will carry geopolitical implications that go far beyond the scientific and engineering challenges we've been discussing. If the first permanent settlers arrive under an American or SpaceX flag, what does that mean for Chinese or Russian or Indian interest in Martian resources and territory? If the settlement grows and begins to assert genuine autonomy, which Earth governments have the standing and the practical leverage to object? If a dispute arises between the settlement and its founding nation or company, what enforcement mechanism exists? You cannot send a police force to Mars on short notice. You cannot impose economic sanctions on a community that is already working towards self-sufficiency. The honest answer is that the legal and political framework for a permanent Mars settlement does not yet exist, and the gap between the speed at which the technology is advancing and the speed at which international governance is evolving creates a situation where the first permanent Martian community may find itself in a genuinely unprecedented legal vacuum. A place where the rules are whatever the people there and the entity that controls their life support systems decide they are. Now let's bring the human dimension back into this, because law and politics are ultimately expressions of human relationships, of power, trust, fear, and identity. Think about what it would mean to be among the first permanent settlers on Mars, knowing that you are not going back, that the community around you is the entirety of your social world, that the organization that brought you there controls every system you depend on to survive. In that context, the relationship between individual autonomy and collective survival takes on a weight that has no real parallel in any human experience we have well-documented frameworks for managing. Closed communities under extreme stress have been studied extensively. Antarctic expeditions, nuclear submarines, isolated research stations, space station crews. The research consistently shows that hierarchical authority structures work reasonably well in short-duration, high-stakes situations, but become increasingly problematic over longer timescales, especially when the hierarchy is perceived as distant, disconnected from local realities, or prioritizing institutional interests over individual well-being. The further a governing authority is from the people it governs, in distance, in understanding, in shared experience, the weaker its legitimacy becomes in the eyes of those people. A Mars settlement governed from Earth by a space agency bureaucracy or a corporate boardroom that has never set foot on the planet, that experiences Martian life only through data streams and reports, will face exactly this challenge, but at an extreme that no previous human governance situation has encountered. The 22-minute communication delay alone effectively prevents any meaningful real-time governance from Earth. Decisions have to be made by the people on the ground, using judgment that Earth cannot second-guess in the moment it matters. Over time, over years and decades, the accumulation of those locally made decisions, the development of local customs and practices and problem-solving approaches shaped by the specific demands of the Martian environment, the growing sense of shared identity among people who have endured extraordinary things together, all of this creates the raw material of a distinct culture, a distinct society, and eventually, perhaps, a distinct political entity. History's most instructive parallel may be less the American Revolution and more the story of Antarctica. The Antarctic Treaty of 1959 established the continent as a scientific preserve, free from territorial claims, governed by the cooperative agreement of the nations conducting research there. It has held together remarkably well for over 60 years, but Antarctica has no permanent population, no economy, no children growing up with their own relationship to that land. Mars will have all of those things, eventually, and once it does, the Antarctic model breaks down. You cannot treat a community of people with children, with history, with economic interests, with political grievances, as a scientific preserve. There is something I want to sit with for a moment here, because it connects everything we've been discussing to something much older and much deeper than space law or orbital mechanics, the question of what we owe each other when the stakes are absolute. In a Mars settlement, the stakes are always absolute. The atmosphere outside is lethal, the temperature outside is lethal, the radiation outside is lethal. Every human being in that settlement is alive because the systems around them are working, because the community around them is functioning, because the fragile web of mutual dependence that holds the habitat together has not broken. In that environment, the social contract is not a metaphor, it is an engineering requirement. Philosophers from Thomas Hobbes to John Rawls have grappled with the question of what kind of social arrangements rational people would choose if they understood the conditions under which they would have to live. Rawls imagined a thought experiment he called the veil of ignorance, choosing the rules of society without knowing what position you would occupy within it. If you designed the governance of a Mars settlement without knowing whether you would be the mission commander or the newest arrival, most skilled engineer or the person struggling with psychological isolation, the one in good health or the one facing a medical crisis, what rules would you choose? What rights would you insist on? What authority would you accept? These are not abstract questions for the settlers who will actually live under those rules. They are daily realities. And the organizations sending people to Mars have a profound moral responsibility, one that goes well beyond the technical checklist of life support systems and launch windows, to have thought carefully about what kind of community they are creating, what kind of power structures they are embedding in that community's foundations, and whether those structures serve the people living within them or the interests of the institution that put them there. Now, let's extend the timeline further, because the political question becomes truly extraordinary when you think not about the first crew, but about the third generation of Martian-born humans. By that point, assuming the settlement has survived and grown, you have people who have never been to Earth, who have grown up under a rust-colored sky, who have never felt natural rain, who have developed their own dialect and their own cultural practices and their own relationship to the landscape around them. People for whom Earth is not home, it is history, a place their grandparents came from, a blue dot in the night sky, somewhat brighter than the other stars, visible from the surface during Martian night in the right season. Those people will have political ideas of their own, needs of their own, a relationship to authority of their own, shaped by the specific pressures and values of a community that has spent generations solving the problem of surviving on a hostile world together, and their connection to any legal or political framework originating on Earth will be at that point essentially sentimental. This is not a crisis, it is a maturation. The same maturation that has happened every time a human community grew distant enough, distinct enough, and self-sufficient enough from its origin to define itself on its own terms. The Martians, and that word, eventually will not be science fiction, will be as real and as legitimate a community as any on Earth, with their own history of hardship and resilience, their own heroes and their own losses, their own relationship to the cosmos seen from a vantage point no Earth human has ever permanently occupied. And here is the thing that strikes me most about that future when I try to imagine it clearly. Those people will look up at the night sky and see Earth, a pale blue star, and feel something that no human being has ever felt before, a connection to that world and a distance from it simultaneously, a nostalgia for a place they have never been, a gratitude for the courage of ancestors who crossed an incomprehensible void to build the world they were born into, and perhaps a curiosity, a yearning that echoes across generations and species and the gulf of space, the same curiosity their great-grandparents felt when they looked up at Mars from Earth and wondered what was there. We are, all of us, creatures of the horizon, and the horizon moves with us wherever we go. There is a fossil sitting in a museum in South Africa that I want you to think about for a moment. It belongs to a creature called Australopithecus sediba. It lived approximately 2 million years ago in what is now the cradle of humankind, a limestone cave system northwest of Johannesburg. It walked upright, used its hands with surprising dexterity, had a brain significantly larger than any ape alive today, and yet it was not human, not quite. It sat at a biological threshold, a moment in the long, branching story of our lineage where the future was genuinely open, where the creature standing in that ancient African landscape could not have known, could not have imagined what its descendants would eventually become. We are those descendants, and we are about to do something that Australopithecus sediba could not conceivably have done. We are about to deliberately place a population of our own species in a radically different environment and leave them there, not for a season, not for a generation, permanently, with the full knowledge that the environment will shape them, biologically, psychologically, culturally, in ways we cannot fully predict or control. We are, in other words, about to become an experiment in our own evolution. And the last time something like this happened to our lineage, the last time a population of early humans was geographically isolated long enough, under different enough environmental pressures to begin diverging meaningfully from the group they left behind, it produced eventually us. Let's talk about what evolutionary biology actually tells us about this process, because there are some common misconceptions worth clearing up before we go further. Evolution does not require millions of years to produce meaningful biological change. That is a comforting myth that makes the process seem safely distant and abstract. The reality is considerably more dynamic. Evolutionary change happens fastest in small, isolated populations under intense selection pressure, exactly the conditions that would characterize the first generations of Martian settlers. The classic example from Earth biology is the Galapagos finches, the birds that Charles Darwin famously observed during his voyage on the Beagle in the 1830s. Different island populations, isolated from one another by stretches of ocean, evolved measurably different beak shapes, body sizes, and feeding behaviors over timescales of thousands to tens of thousands of years. The environmental pressures on each island, the specific food sources available, the specific competitors present, the specific climate conditions, drove the populations in different directions from a common ancestor. A more dramatic example involves human beings themselves. The lactase persistence gene, the genetic variant that allows many adult humans to digest milk, spread through certain human populations in Europe and Africa within the last 10,000 years, driven by the selective advantage it provided to communities that had domesticated cattle. 10,000 years is an eye blink in evolutionary time. It is also, roughly speaking, the timescale over which a Mars settlement might grow from a handful of pioneers to a population of tens of thousands. Meaningful genetic change in a small isolated population under strong selection pressure is not merely possible on that timescale. It is expected. The selection pressures on Mars are not subtle. Every day on the Martian surface, radiation is filtering through inadequate shielding and interacting with cellular DNA. Individuals with genetic variants that confer even slightly greater resistance to radiation-induced DNA damage will, on average, survive longer and reproduce more successfully than those without. Over generations, those variants will become more common in the population. This is natural selection operating in real time, in a direction specifically dictated by the Martian environment. The low-gravity environment will favor individuals whose cardiovascular systems, skeletal structures, and muscular development are naturally better suited to the reduced gravitational load. The psychological demands of confinement, isolation, and high-stakes cooperative living will favor temperamental and cognitive traits that allow individuals to maintain emotional stability and productive social relationships under extreme conditions. The specific nutritional environment, whatever combination of locally grown crops and manufactured supplements the settlement can provide will create selection pressures around metabolic efficiency and nutritional flexibility that differ substantially from those of any Earth population. None of this happens in one generation, but the direction of travel is clear from the very first child born on Mars, and the cumulative effect, sustained over many generations, points toward a population that is measurably physiologically different from the humans who first arrived. Now let's layer onto that biological divergence something that accelerates the process in ways that are genuinely unprecedented in the history of our species: genetic technology. The settlers on Mars will not be passive subjects of natural selection. They will be among the most technologically sophisticated human beings in history, with access to tools for understanding and potentially modifying the human genome that would have seemed like magic to any previous generation. CRISPR-Cas9, the gene-editing technology that earned Jennifer Doudna and Emmanuelle Charpentier the Nobel Prize in Chemistry in 2020, allows specific sequences of DNA to be identified and altered with a precision and accessibility that was unimaginable 20 years ago. The technology is advancing rapidly. Its applications in medicine, treating genetic diseases, developing cancer therapies, potentially eliminating inherited conditions, are already moving from laboratory to clinic. In the context of Mars settlement, the temptation to use this technology proactively is obvious. If you know that radiation exposure is the single greatest biological threat to your community's long-term survival, and if you have the tools to identify and potentially enhance the genetic variants associated with DNA repair efficiency and radiation resistance, the question of whether to use those tools becomes very pressing very quickly, particularly in a community that is physically isolated from Earth's regulatory frameworks, legal systems, and bioethical oversight bodies. No nation on Earth currently permits germline genetic modification, changes to the DNA of embryos that would be inherited by all subsequent generations for enhancement purposes rather than disease prevention. The scientific community has broadly agreed that the technology is not yet mature enough and the ethical questions not yet sufficiently resolved to justify crossing that line. A landmark and deeply controversial case in 2018, in which a Chinese researcher named He Jiankui claimed to have created the world's first gene-edited babies, twin girls whose CCR5 gene was modified in an attempt to confer resistance to HIV, was condemned internationally and resulted in He's criminal prosecution in China. But a Mars settlement operating beyond the practical reach of Earth's legal and ethical oversight bodies may face a calculation that is fundamentally different from anything any bioethics committee on Earth has had to make. When the alternative to genetic intervention is watching your community slowly accumulate radiation-induced cancers and neurological damage across generations, when the stakes are the literal survival of the settlement, the ethical calculus shifts in ways that are deeply uncomfortable to contemplate. This is not a hypothetical risk that belongs in the distant future. It is a question that would arise within the first generation of settlement as the medical data from living on Mars accumulated and the long-term biological consequences became undeniable. And the answer the settlement reaches, whatever it is, will shape the biological trajectory of the Martian population for all subsequent generations. If they choose to intervene, to deliberately modify the germline of their descendants to better suit the Martian environment, they will be making the most consequential biological decision in the history of our species. They will be, in a very literal sense, designing a new kind of human being, one built for Mars rather than Earth, one that carries the genetic legacy of Earth life, but has been deliberately shaped away from it towards something new. And if those modifications are significant enough and sustained across enough generations, the biological definition of species membership, which hinges on the capacity for successful interbreeding, may eventually be affected. A population that has been genetically modified for Mars and then further shaped by generations of natural selection in the Martian environment may reach a point where interbreeding with unmodified Earth humans produces offspring with reduced viability or fertility. That is the technical definition of speciation, and it would mean that the human family, the single species that has covered this planet from pole to pole, that built every civilization, that looked up at every star, had become two. I want to pause here and acknowledge something, because this territory, the possibility of deliberate human genetic modification in a context beyond conventional oversight, is deeply uncomfortable. It should be. The history of the 20th century contains horrifying examples of what happens when powerful groups decide they have the right to determine who gets to reproduce and in what direction the human genome should evolve. Eugenics programs caused immense suffering and ended lives that deserve to be lived. The horror of those programs should make us profoundly cautious about any framing that treats the human body as a design problem to be optimized. The difference, and it is a meaningful difference, though not a complete absolution, is consent and context. The eugenics programs of the 20th century were imposed by states on populations who had no say in the matter, often targeting people on the basis of race, disability, poverty, and other characteristics that had nothing to do with genuine genetic fitness. What we are discussing in the context of a Mars settlement is a community making decisions about its own biological future, in a context where the stakes are genuinely existential, with full knowledge of the science and the ethics involved. That difference is real. But the discomfort is appropriate, and the ethical framework for making these decisions, if they are ever to be made responsibly, needs to be developed now, before the technology and the circumstance converge in ways that make careful deliberation impossible. Now let's zoom out from genetics and think about something broader, something that the fossil record and the deep history of life on Earth tell us about what happens when populations separate and diverge. The history of life is a history of branching. Every species alive today is the product of an unbroken chain of branching events stretching back approximately 3.8 billion years to the first self-replicating molecules in the ancient ocean. Every branch point represents a moment when a population divided by geography, by behavior, by some shift in environment, and the two resulting groups began walking different evolutionary paths. Most of those branches eventually ended in extinction. A few of them led, through extraordinary chains of contingency, to the diversity of life we see today. Homo sapiens emerged from this process roughly 300,000 years ago in Africa. We then spread across the planet in waves of migration, crossing deserts and mountain ranges and ocean channels, adapting behaviorally and eventually biologically to an extraordinary range of environments. The genetic diversity within the human species today, remarkable as it is actually relatively modest compared to many other species, partly because of the relatively recent origin of our species, and partly because of population bottlenecks that periodically reduced genetic diversity throughout our evolutionary history. A Mars settlement represents a new kind of bottleneck, a founding population of perhaps dozens to hundreds of individuals carrying a non-random sample of Earth's genetic diversity, selected specifically for health, intelligence, psychological resilience, and technical capability, establishing themselves in a radically new environment. Population geneticists call this a founder effect. The genetic characteristics of the founding population, including rare variants that might be present at very low frequencies in the Earth population, will be overrepresented in all subsequent Martian generations simply because of chance. combined with the selection pressures of the Martian environment. The founder effect could produce a genetically distinctive Martian population within a surprisingly small number of generations. The novelist Kim Stanley Robinson explored this territory with extraordinary depth and scientific rigor in his Mars trilogy, Red Mars, Green Mars, and Blue Mars, published in the 1990s. Robinson spent years researching the science before writing, and his portrait of the first 100 colonists and their biological and cultural evolution over generations remains one of the most scientifically grounded works of fiction ever written about human planetary settlement. His depiction of the tension between those who want to preserve Mars in its natural state and those who want to transform it, terraform it, to make it more habitable for unprotected humans captures something real about the ethical divisions that would fracture any actual Mars community. Terraforming. That word deserves its own moment. The idea of terraforming Mars, deliberately modifying the planet's atmosphere, temperature, and surface conditions to make it more Earth-like, has been seriously discussed by planetary scientists since at least the 1960s. Carl Sagan himself wrote about the possibility in 1973, proposing that certain microorganisms might be introduced to the Martian polar caps to produce greenhouse gases and begin warming the planet. Modern terraforming proposals vary enormously in ambition and timescale. The most modest involve creating local sheltered environments, pressurized valleys or dome-covered craters, where a thicker atmosphere can be maintained artificially. The most ambitious envision a full planet transformation over timescales of centuries to millennia, releasing enough greenhouse gases to warm the planet, thickening the atmosphere to the point where liquid water is stable on the surface, eventually introducing plant life to produce oxygen, and over thousands of years creating conditions where unprotected humans could walk on the surface. The physics of full-scale terraforming Mars faces significant challenges that are worth being honest about. Mars lost its global magnetic field billions of years ago. Without that field, the solar wind, the continuous stream of charged particles flowing outward from the Sun, would gradually strip away any atmosphere thick enough to support life, just as it stripped away Mars's ancient, thick atmosphere over hundreds of millions of years. Maintaining a terraformed Martian atmosphere over geological timescales without a planetary magnetic field to protect it may require either finding a way to generate an artificial magnetosphere, proposals for which exist but remain deeply speculative, or accepting that the terraformed state is a temporary condition requiring continuous maintenance rather than a permanent transformation. There is also the ethical dimension that becomes enormously more complicated if Mars harbors extant life. Terraforming a living Mars, even if the life is microbial, even if it exists only in isolated subsurface pockets, would constitute the deliberate alteration and possibly elimination of an entire biosphere. That is a moral question of a magnitude that no human civilization has previously had to grapple with. We have driven species to extinction on Earth through carelessness and exploitation. But the deliberate transformation of an entire planet's environment, with full knowledge that doing so might eliminate the only other life in the known universe, would be something categorically different. Some astrobiologists argue that if Martian life exists and we discover it, all plans for human settlement, let alone terraforming, should be suspended indefinitely, pending a complete scientific characterization of that life and an international consensus on what to do. Others argue that the needs of a growing human population with a finite home planet must take precedence over the preservation of what might be nothing more than ancient, barely surviving microbial communities in a subsurface niche. Still others suggest that Martian microbes, if they exist, might actually be our distant relatives, the product of the same primordial chemistry that produced life on Earth, perhaps even transferred between the two planets billions of years ago via asteroid impacts in a process called lithopanspermia. If that is true, then terraforming Mars to support human life might be less an act of conquest and more an act of homecoming. The scientific and philosophical complexity here is genuine. And the decisions that will eventually be made by governments, by companies, by settlers on the ground will reverberate through the history of life in this solar system for as long as that history continues. Let me bring this back to the individual human being, because it is very easy, in a conversation this large, to lose sight of the person inside the story. Imagine you are one of the first settlers. You have been on Mars for 3 years. You have watched dust storms roll across the horizon like living walls of rust-colored shadow. You have grown food under lights in a sealed room and eaten it for the 1,000th time. You have repaired equipment in a suit that makes every movement effortful, with gloves so thick that the delicate haptic feedback your hands expect from the world is replaced by a muted, blunted approximation. You have watched your body change in ways that the medical briefings told you to expect, but that still feel strange and alienating when you notice them in the mirror. You have had conversations with people on Earth that are shaped by the 44-minute round-trip delay into something more like the exchange of letters than actual dialogue. And you have also, because the human capacity for wonder does not require comfort or convenience, watched the moons of Mars cross the sky at speeds that no moon on Earth can match. Phobos, the larger of the two, rises in the west and sets in the east, moving so quickly across the Martian sky that it completes a full orbit in just 7 hours and 39 minutes, faster than the planet beneath it rotates. You have watched sunrises where the sky turns blue near the sun while remaining pink at the horizon, the opposite of Earth, because of the way fine Martian dust scatters light. You have stood in a silence so profound that the universe feels close enough to touch, and you have looked at a blue star in the Martian night sky and felt something for which there may not yet be a word. The feeling of being far from home and being exactly where you are supposed to be, simultaneously, that feeling, that impossible, beautiful contradiction, may be the most specifically human thing about this entire enterprise. The capacity to be homesick and purposeful at once, to grieve what you have left and be grateful for where you are, to hold the smallness of your individual life and the vastness of your cosmic context in the same breath, without being destroyed by either. We are the species that does this, that has always done this, that walked out of every homeland it has ever known and kept walking, not because the next place was necessarily better, but because the act of walking toward the unknown is, for us, a form of being fully alive. There is a question that astronauts get asked more than almost any other when they return from space. Do you want to go back? And the answer, almost universally, across decades of human spaceflight, across wildly different personalities and backgrounds and missions, is yes. Not a polite yes, not a diplomatic yes, shaped by the expectations of the interviewer. A yes that comes from somewhere deeper than preference or ambition. A yes that sounds, when you hear it from someone who has actually been there, less like a desire and more like a recognition, like the acknowledgement of something that was always true but could only be confirmed by the experience itself. Now imagine asking that question to someone who has not spent 6 months in low Earth orbit, 400 kilometers above the planet, with the blue curve of home always visible below them. Imagine asking someone who has spent 3 years on Mars, who has watched 2 Martian winters pass, who has buried a colleague in soil that no undertaker from Earth has ever touched, who has seen their own face in the mirror change in ways that mark the passage of time on a world with a different calendar, who has learned the specific quality of Martian light at the specific hour of the Martian afternoon that has become, without any deliberate decision, their favorite time of day. Ask that person if they want to go back to Earth and listen very carefully to the silence before they answer. I want to be precise about what we mean by choice here, because the first humans on Mars may not have a clean choice at all, not in the way we usually use that word. The orbital mechanics, the fuel requirements, the physiological changes, the launch windows. All of these constraints mean that the decision about whether to return is not entirely theirs to make. It is shaped by physics and engineering and timing in ways that remove much of the conventional freedom from the word choice. But within those constraints, within the window of genuine agency that remains, something interesting happens. Something that the psychological research on extreme environments points toward, and that the accounts of long-duration explorers across human history corroborate. Something that has to do with the relationship between identity and place, between belonging and becoming, that is one of the oldest and most powerful dynamics in human experience. The phenomenon has been observed in Antarctic winter-over cruise, in long-duration submarine deployments, in the accounts of explorers returning from years in remote and hostile environments. After a certain threshold of time and shared hardship, the place you are in stops being foreign. It stops being an obstacle or a backdrop or a temporary address. It becomes, in the most fundamental psychological sense, yours. Not because you own it in any legal or territorial sense, but because you have suffered in it and worked in it and laughed in it and grieved in it long enough that it has become part of the story you tell about yourself. Ernest Shackleton's crew, stranded on the ice of the Weddell Sea for nearly 2 years after their ship Endurance was crushed by pack ice in 1915, did not simply endure their ordeal. They built a life within it. They organized routines and entertainments and social rituals that gave shape and meaning to days that could otherwise have been simply terrifying. When they were finally rescued, several of the men described a feeling that was not pure relief. It was mixed with something harder to name, a loss as well as a return, because the life they had built on the ice, however brutal, was theirs in a way that life back in civilization would take time to reclaim. Now scale that experience across years, across generations, across a community rather than a small expedition crew, and across a distance that makes return not merely difficult, but possibly physiologically impossible. The psychological process of adopting Mars as home is not a resignation or a defeat. It is a form of flourishing, the human capacity to make meaning, to build belonging, to find beauty in even the most extreme and alien of environments. It is one of our most extraordinary and underappreciated attributes as a species. Let's talk about what neuroscience actually tells us about home, because the concept of home is not just a sentiment, it has a biological substrate, a neural architecture, and understanding that architecture helps us understand what happens when you take a human being and place them in an environment that their nervous system has never experienced before. The hippocampus, the brain region most associated with spatial memory and navigation, builds what neuroscientists call cognitive maps, mental representations of space that allow us to navigate familiar environments with an ease and efficiency that we almost never consciously notice until it is disrupted. When you walk through your home in the dark without turning on the lights, you are using a cognitive map built from thousands of repeated experiences of that space. The map is so deeply embedded that conscious navigation is unnecessary. When you move to a completely new environment, a new city, a new country, a new cultural context, the hippocampus has to build new maps from scratch. The process is effortful and cognitively demanding, which is part of why moving to a new place is psychologically exhausting, even when it is also exciting. Over time, Over months and years of repeated experience, the new environment becomes neurologically familiar. The maps consolidate. The place starts to feel like home, not because of any conscious decision, but because the brain has done its work. On Mars, this process would unfold in an environment that provides the hippocampus with an entirely novel set of spatial inputs, the specific quality of light at different times of the Martian sol, the particular distances and proportions of the habitat corridors, the view from each viewport, the way Phobos moves across the night sky, the color of dust on the equipment after an EVA. All of these experiences, repeated daily across years, would be encoded into a cognitive map as detailed and as neurologically real as the map of any childhood home on Earth. And here is the extraordinary implication. A person who has lived on Mars long enough, who has built those maps, who has encoded that landscape into the deepest structures of their memory and spatial cognition, would, if they were somehow transported back to Earth, experience Earth as foreign. The gravity would feel crushing. The noise of a populated planet, the sensory richness of wind and rain and biological sound would be overwhelming after years of Martian quiet. The vast open sky, without the familiar amber tint, without the visible moons moving at their characteristic speeds, would be wrong in ways that are neurologically specific and emotionally profound. Home is not where you came from. Home is where your brain learned to be, and for the first humans on Mars, if they stay long enough, that will be true in the most literal neurological sense. Their brains will have learned Mars. Earth will be the foreign country. Now let's think about what they will have seen, what they will know about the universe from that particular vantage point that no human being has ever known before. The night sky from Mars is different from the night sky you see from Earth, not dramatically so. The stars are the same stars, the constellations are the same constellations, because Mars is close enough to Earth, in astronomical terms, that the stellar parallax is essentially invisible to the naked eye. But several things are different in ways that matter. The Milky Way, the band of our galaxy's disk that stretches across the dark sky on a clear night, is visible from Mars with the same breathtaking clarity as from Earth's darkest locations, perhaps more so because the Martian atmosphere, though thin and dusty, scatters significantly less light than Earth's thicker air. The galactic core, the dense star clouds of Sagittarius, the dark dust lanes threading through the bright star fields, all of it visible with the naked eye in a way that most Earth humans living in light-polluted cities have never experienced. Jupiter is bright from Mars, a brilliant point of light, easily visible even in the Martian twilight. Saturn is fainter but still clearly present. Earth, the pale blue star we keep returning to, is visible near the Sun, best seen in the Martian dawn or dusk sky. It would never be far from the Sun as seen from Mars, no more than about 47 degrees of separation at maximum elongation, and so the first humans on Mars would see their home world the way we see Venus from Earth. An evening star, a morning star, brilliant, blue-white, unmistakable, and unreachable for all practical purposes, except through the light that travels across the void between them at 300,000 kilometers per second. There is something that I find almost unbearably poignant about that image. A human being standing in a Martian habitat at the end of a long sol, looking out through a viewport at a pale blue star hanging in the amber evening sky, knowing that every person they have ever loved who is still alive is somewhere on that tiny point of light, that their childhood home, their parents, their closest friends, the places that made them, all of it is contained in that star, separated from them not just by distance but by physics, by the brutal mathematics of orbital mechanics and rocket fuel and launch windows that open every 26 months. And yet, and this is the part that the poets and the philosophers will one day work through in ways I cannot do justice to here, That same person looking at that blue star is seeing something no human being in the history of our species has ever seen before. They are seeing Earth the way Earth sees Mars, from the outside, as a world among worlds. Not as home in the unconsidered way that home usually works, invisibly, by default, without examination, but as a conscious choice, a deliberate recognition of what it is and what it means. Carl Sagan, in his reflection on the famous pale blue dot photograph taken by Voyager 1 in 1990, wrote some of the most important sentences any human being has ever written about our place in the cosmos. He described Earth as a mote of dust suspended in a sunbeam. He argued that our planet is a lonely speck in the great enveloping cosmic dark, and that in our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. He used that image, that small, fragile, impossibly beautiful point of light, to argue for the importance of treating each other with greater kindness, for the absurdity of the violence and division with which we have filled so much of our brief time on that pale blue dot. The first humans on Mars will know that feeling from the inside. They will feel the smallness of Earth not as an abstraction, not as a philosophical position adopted from a book, but as a direct perceptual experience. They will know, in their bones, that the entirety of human civilization, the full scope of human history, every war and every symphony and every love affair and every act of cruelty and every act of extraordinary compassion, all of it happened on a world small enough to cover with an outstretched thumb. And they will know something else, something that changes the relationship between that knowledge and despair. They will know that human beings left that world, voluntarily, deliberately, carrying that history with them across the void, and built something new on the other side. That act, the act of leaving and building, is one of the most definitively human things I can imagine. It connects the first Martian settlers to every explorer, every migrant, every refugee, every pioneer in the long human story. The specific technology is unprecedented. The specific destination is unprecedented. But the impulse, the reaching towards something beyond the known horizon in the full knowledge that you may not return, is as old as our species. Older, probably. It is woven into our evolutionary history in the way that migration shaped early Homo sapiens across hundreds of thousands of years of walking out of Africa and into a world they had never seen. We are not a species that stays. We are a species that goes, and then goes again, and builds, and fails, and builds again. The question of whether the first humans on Mars would want to come back is, at its deepest level, a question about identity, about what kind of story a person tells about themselves, and what chapter of that story they are living when the question is asked. In the early years, the first months, perhaps the first year, the answer might genuinely be yes. The body is still calibrated for Earth. The emotional landscape is still organized around Earth relationships and Earth memories. The cognitive maps of home are still fresh and accessible. Homesickness, under those conditions, is not a weakness or a failure. It is a biological reality. The brain is doing exactly what it is supposed to do, registering the gap between the environment it was built for and the environment it currently occupies, and generating the emotional signal that says, this is not right, go back. But the brain is also adaptable, extraordinarily adaptable, the same plasticity that allows human beings to learn languages, to acquire skills, to recover from trauma, to form bonds with strangers who become family. That plasticity is working continuously in the Martian environment, reshaping the cognitive and emotional landscape to fit the new reality. And over time, not overnight, not in a month, but over the long accumulation of souls and seasons and shared experiences that constitute a life, the brain's model of home begins to shift. By the third year, the answer to the question might be more complicated. Yes, in the sense that Earth is still where the people they love most are still living, but also Not entirely. Because something on Mars has become irreplaceable, the specific quality of light, the specific rhythms of the community, the specific satisfaction of the work, the daily, concrete, meaningful work of keeping people alive in a place that does not want them to be. And by the 5th year, the 10th year, if the mission has survived, if the community has grown, if children have been born and raised in that amber-lit world, the answer might be something closer to no. Not because Earth has been forgotten or stopped being loved, but because home has moved. Because the story the settler tells about themselves is no longer a story about leaving something behind. It is a story about building something that did not exist before, and you do not leave the thing you built. You tend it, you protect it, you pass it on. There are philosophers who argue that the deepest form of human freedom is not the freedom to go wherever you want. It is the freedom to choose, consciously and deliberately, where you belong, to commit to a place and a community and a purpose with full knowledge of what you are giving up, and to find in that commitment not a diminishment of your possibilities but an expansion of your meaning. The first humans on Mars will live that philosophy in its most extreme possible form. They will have given up more than any explorer in human history. They will have committed to a place that tested them at every level: physical, psychological, biological, social, spiritual. And if they survive, if the community takes root and grows and endures, what they will have built is not just a settlement, not just a collection of pressurized habitats and hydroponic gardens and nuclear reactors on a red plain. They will have built the first chapter of a story that could last as long as the universe allows. The first word in a language that does not yet have a name. The first heartbeat of a civilization that will one day look back on the 21st century the way we look back on the first humans crossing the land bridge from Siberia to Alaska, with awe at the audacity, with gratitude for the courage, and with the particular tenderness we reserve for the moments when our ancestors did something extraordinary and did not know, could not know, how extraordinary it was. So, would the first humans on Mars come back? Some of them, the ones whose bodies still can, whose launch windows align, whose mission architecture includes a return vehicle, might. The ones who went as explorers rather than settlers, the ones whose work was specifically defined as temporary, the ones for whom the pull of Earth, family, relationships, the specific gravity of the world that made them, turns out to be stronger than the pull of the horizon, and some of them will not, cannot, would not, even if the physics allowed it, because they will have become something that has no name yet, not fully Earth human any longer, not in the physiological sense, not in the neurological sense, not in the deepest sense of where home lives in the body and the mind, and not yet Martian in any established cultural or biological sense. Something in between, something new. The first members of a category that human history has never had to make room for before, the first people for whom another world is simply where they live. Every story needs an ending. But the best endings are not really endings at all. They are the moment when the story you thought you were following reveals itself to be a much larger story, one that was always there, just beyond the edge of what you could see from where you were standing. One that does not close when the final page turns, but opens outward into something that does not have edges yet. This is that moment. We have spent this entire video walking through the reasons why the first humans on Mars would not come back. The physics of the rocket equation, the brutal, unforgiving mathematics that makes the return journey from Mars one of the most energetically expensive things a human civilization could attempt. The biology, the bone density loss, the cardiovascular changes, the radiation accumulating in living tissue, the body rewriting itself in response to a gravity field that is 38% of Earth's. The psychology, the way the mind builds new maps of home, the way belonging migrates from the place you left to the place you stayed, the way identity reshapes itself around the life you are actually living rather than the life you left behind. The politics, the governance vacuum, the communication delay that makes real-time authority from Earth a fiction, the historical inevitability of communities growing beyond the reach of the institutions that created them, the philosophy, the deep question of what choice means when the constraints are absolute and what freedom means when the horizon is the surface of another world. We have walked through all of it, and I want to make sure before we finish that we have understood what all of it adds up to, because individually each of those factors is a challenge, a problem to be solved or at least managed. The engineers will work on the fuel problem. The medical teams will develop countermeasures for the physiological changes. The psychologists will design better social structures and mental health support systems. The lawyers and diplomats will eventually negotiate the governance frameworks that do not yet exist. But collectively, all of those factors working simultaneously, reinforcing each other, compounding across time, they point towards something that is not a problem to be solved. They point toward an outcome, a destination that the logic of the whole enterprise is moving toward with a kind of inevitability that transcends any single technical or political obstacle. They point toward permanence. Let me be specific about what I mean by permanence, because I do not mean it as a tragedy. I do not mean it as a failure of engineering or will or funding. I mean it as the natural, perhaps inevitable, result of doing something genuinely unprecedented with genuine commitment. When you send human beings to Mars with the intention of building a lasting presence there, not a temporary outpost, not a flags and footprints moment, but an actual community with the infrastructure and the social architecture to sustain itself and grow, you are not just sending explorers, you are planting a seed. And seeds, if the conditions are right, do not stay seeds. They become something else. Something that has its own logic, its own requirements, its own relationship to the environment it grows in. Something that cannot be unplanted once it has taken root. The first permanent Martian settlers will go knowing this, at least intellectually. They will have read the mission documents. They will have attended the briefings. They will have signed the agreements that acknowledge, in whatever legally careful language the mission architects have devised, that return is not guaranteed, that it may not be possible, that the mission's success is defined not by the ability to come home, but by the ability to stay. And then they will go, and the living of it will teach them things that the reading and the briefings and the agreements could not. It will teach them what it feels like to wake up every morning knowing that the only way through is forward, that there is no rescue coming from Earth on any human timescale, that the community around them is not a temporary arrangement of colleagues, but the permanent fabric of their social world, that the choices they make about how to allocate resources, how to resolve conflicts, how to raise children, how to grieve the dead, how to celebrate the things worth celebrating in a place where celebration requires conscious effort, are the choices that will define not just their own lives, but the culture of every Martian generation that follows. That knowledge, that specific, weighty, clarifying knowledge, is something no amount of simulation or training on Earth can fully replicate. It is the knowledge that comes from the skin, from the body, from the part of the nervous system that understands stakes in a way that the intellect alone cannot access. And the people who carry that knowledge and build lives within it rather than being destroyed by it will be among the most remarkable human beings who have ever lived. I want to talk about legacy, because it is one of the things that motivates the most ambitious human endeavors, and because the legacy of the first Martian settlers will be unlike any legacy in the history of our species. Think about the figures from human history whose decisions shaped the world in ways that echo centuries later. The navigators and cartographers of the age of exploration who mapped coastlines that had never been seen by European eyes and opened trade routes that restructured the entire global economy. The scientists of the scientific revolution, Copernicus, Galileo, Newton, Kepler, who replaced a cosmos centered on human importance with a cosmos ordered by mathematics and indifferent physical law, and in doing so gave us tools for understanding reality that still underpin every technology we use today. The engineers of the Industrial Revolution, who harnessed energy in ways that transformed not just production, but the entire social organization of human life. The physicists of the 20th century, who cracked open the structure of matter and energy and gave humanity both nuclear weapons and nuclear medicine, both the transistor and the computer. Each of these figures made choices whose consequences they could not fully foresee, in contexts that did not yet have the frameworks to evaluate what they were doing. They worked at the edge of the known, and in doing so they moved the edge. The first humans on Mars will be doing the same thing, except that the scale of what they are beginning is larger than any of those precedents. Because they are not just moving the edge of knowledge, or the edge of technology, or the edge of social organization. They are moving the edge of where life exists in the universe. For the entirety of the 3.8 billion year history of life on this planet, through every mass extinction and every evolutionary radiation and every catastrophe and every flowering of biological complexity, life has been confined to a single world. One planet, one pale blue dot in the vast indifference of space. Everything that has ever lived, everything that has ever breathed or grown or reproduced or evolved, all of it happened here. On this one fragile, finite, irreplaceable world, the day a human being takes their first breath on Mars, their first breath sustained by technology rather than biology, in a habitat that has no right to exist on a world that did not invite it, that changes. Not immediately, not dramatically. The universe does not notice, the cosmos does not care. But something has shifted at the level of principle that no subsequent catastrophe, no extinction event, no stellar cataclysm can entirely undo. Life has demonstrated that it can reach beyond its birthplace, that the barrier between worlds is not absolute, that the story of life in this solar system is no longer confined to a single chapter. That is a legacy that belongs not to any nation, not to any company, not to any mission director or rocket engineer or policymaker. It belongs to the people who were actually there, who woke up on Mars in the early light of a Martian morning and made breakfast and checked the life support systems and did the work. The irreplaceable, unglamorous, essential, daily work of being alive in a place where being alive requires everything you have. Now I want to turn the question around, because we have spent most of this video thinking about what it means for the people who go. And I think it is equally important, maybe more important, to think about what it means for the people who stay, for us. Because if the first humans on Mars are the seed, we, the civilization that grows them, that funds the mission, that builds the rockets, that develops the technology, that makes the political and financial and ethical decisions that shape the enterprise, we are the soil. And the kind of civilization that is capable of sending humans permanently to Mars is necessarily a civilization that has made certain choices about what it values. It has chosen to invest in a future that it may not live to see. It has chosen to accept that some of its members will go and not return, and to find in that sacrifice not a tragedy to be avoided, but a contribution to be honored. It has chosen to care about the long-term survival of our species and our civilization over the short-term comfort of keeping everything familiar and close and within the reach of a rescue mission. These are not small choices. They are not politically easy or economically obvious or emotionally uncomplicated. Every dollar spent on Mars is a dollar not spent on hospitals or schools or climate adaptation or the 1,000 urgent, visible, immediately important problems that press on every government every day. The opportunity cost of a Mars settlement program is real, and anyone who discusses the enterprise honestly has to acknowledge it. But the argument for going, the argument that the most serious proponents of Mars exploration have consistently made, is not that Mars is more important than the problems of Earth. It is that the long-term survival of the species and the civilization requires redundancy, requires that we not keep all of our biological and cultural eggs in a single planetary basket. The Earth has been hit by asteroids before. The Chicxulub impactor 66 million years ago ended the reign of the non-avian dinosaurs and wiped out approximately 75% of all species on Earth. The Permian extinction, 252 million years ago, killed approximately 96% of all marine species and 70% of terrestrial vertebrate species. The closest life on Earth has ever come to total elimination. These are not hypothetical risks. They are documented facts in the geological record. The Earth is a dangerous place on long timescales, and the biological diversity that has survived to the present day, including the particular branch of the primate family tree that eventually produced us, has survived not because the Earth has been uniformly kind, but because it has been resilient, because life finds a way to persist, to diversify, to inhabit every available niche, and to recover from catastrophes that seem terminal. The argument for Mars is, at its most fundamental level, an argument for applying that same logic deliberately, intentionally, before the catastrophe rather than after, taking the capacity for resilience that evolution built into life over billions of years and extending it by an act of conscious will to a second world. That is not a trivial argument. It does not resolve every competing priority or answer every urgent question about how to allocate resources in a world full of immediate suffering, but it is a serious argument made by serious people, rooted in a genuine understanding of what the long-term trajectory of life on a single planet looks like when measured against geological time. Let me tell you about a concept that comes from information theory and that I think is deeply relevant here. It is called redundancy. In information systems, redundancy means storing the same data in multiple locations so that if one location fails, if the server crashes, if the hard drive corrupts, if the building burns down, the data is not lost. It survives in its copies. The system continues. The most important information system in the known universe is the biosphere of planet Earth. It stores in the DNA of every living organism the accumulated result of 3.8 billion years of evolutionary experimentation. It contains, in the cultural memory and accumulated knowledge of human civilization, the product of hundreds of thousands of years of learning how to survive and create and understand. All of that information exists currently in a single location, one planet, one fragile, beautiful, irreplaceable world with no backup copy anywhere in the universe. A permanent human settlement on Mars is, from this perspective, the beginning of a backup, not a replacement, not an escape from responsibility for the care and preservation of Earth, a redundant copy, a second location for the most precious information in the universe. The people who go to Mars and do not come back are not abandoning Earth, they are protecting it. They are ensuring that if the worst happens, if the asteroid comes, if the supervolcano erupts, if the climate destabilizes beyond recovery, if the pandemic arrives that no medicine can stop, something survives, something carries forward. The story does not end. That reframing matters, because it transforms the one-way mission from a sacrifice into an act of stewardship, from a loss into a gift, not just to the people who will live on Mars, but to every future generation of life in this solar system, wherever it ends up living. I want to end with something personal, or as personal as a video like this can be. I make these videos because I believe, genuinely, without reservation, that the universe is the most extraordinary thing there is, that the fact of its existence, the fact that it has the properties it has, the fact that those properties gave rise to chemistry, and then to biology, and then to consciousness, and then to the particular form of conscious, self-aware, cosmically curious life that is sitting here right now asking these questions, that this is something worth being astonished by every day, without getting used to it. And I believe that the story of humanity's relationship with the cosmos is still in its very early chapters, that everything that has happened so far, every civilization, every scientific revolution, every technological leap, every moment of genuine contact between the human mind and the deep structure of reality is prologue, is set up, is the universe slowly building the conditions for something that does not yet have a name. Mars is the next page, not the destination, not the endpoint, not the answer to any of the deep questions that drive this journey, but the next page, the moment when the story that started around a fire somewhere in Africa, sometime in the deep past of our species, takes a turn that makes everything that came before it look like preparation. The first humans on Mars will be frightened, they will be lonely. They will miss people they love with an intensity that the 22-minute speed of light delay makes simultaneously worse and more manageable. Worse because real comfort is impossible. More manageable because the delay creates a kind of enforced equanimity. You learn to hold your fear and your grief and your homesickness in a container that is yours alone, because the person on the other end of the message will not receive it for 11 minutes and will not be able to respond for another 11. You learn to be self-sufficient in the emotional sense, in the same way you are already self-sufficient in the physical sense. And they will also, in the specific way that human beings always do when they are placed in conditions that require the full deployment of everything they are, be more fully alive than they have ever been, more present, more aware of each moment, more grateful for the things that work, more creative in solving the things that do not, more connected to the people around them, because those people are all they have. And sometimes, in the quiet moments that any life contains, however extraordinary its circumstances, they will step into whatever serves as their equivalent of a backyard, and they will look up at a sky the color of rust at the horizon and deep violet at the zenith, and they will see the moons moving and the stars burning cold and clear through the thin air, and they will feel something that no human being in the history of our species has ever felt. They will feel at home, not on Earth, on Mars, on a world that never had a name for the feeling of home, because nothing alive had ever been there long enough to give it one until them. So here is the final answer to the question we started with: would the first humans on Mars come back? Some will. The ones who went to explore rather than to stay. The ones whose bodies still permit it. The ones for whom Earth's gravity, emotional, biological, relational, remains stronger than the gravity of the new world. But the ones who matter most to the story, the ones who shape everything that comes after, will not, cannot, and eventually would not, even if every obstacle were removed and the door home stood open. Because home will have moved, because they will be the living proof that the most human thing we do is not stay in safety. It is reach toward the unknown with everything we have, full knowledge of the cost, and find, on the other side of the fear, on the other side of the void, on the surface of a world that never asked for us, that we were capable of more than we knew we always were. We are made of the same atoms that formed in the hearts of stars billions of years before the Earth existed. We carry in our DNA the memory of every ancestor that survived every catastrophe life has thrown at this planet across nearly 4 billion years. We inherited from those ancestors and from the particular improbable journey that led to us, a brain that can look at the universe and ask why, that can imagine its own future, that can choose freely and deliberately to reach toward a horizon that may not welcome it and build something there that did not exist before. That is what we are, and Mars is just the next place we will prove it. And if you think Mars sounds tough now, wait until you see what daily life there actually looks like. Click the video on your screen right now. We explore why Mars would be a horrible place to live. And I promise, it will change the way you see the red planet forever. Trust me, you do not want to miss this one. See you there.